Where's Natasha? I'll steal her microphone. Well, my question was, does this microphone work? But I'll steal hers that she's chairing. Yes, okay. Sorry. Are we ready, Natasha? So, geez. What? Neutral hydrogen burns around galaxy from the SKA era. Okay. Can I set up the screen share, please? Thanks. Now it's on me to figure out how to do it. So I see it in the Zoom, but not on the screen here. There we go. Thank you. Am I just going to start things, Natasha? Okay. So welcome everyone to the session. I have just a couple of minutes to very quickly welcome you. I think I've already hopefully welcomed many of you at our plenary. And I will be fast because our schedule is packed. So we will adhere to time limits, please, and to try to arrive on time. I know it's a big meeting with a lot happening. I do encourage people to sit in the front half of the room. This is a very long room. And especially if you're going to ask questions, if you're sitting in the back, if you can help our volunteers and microphone holders out by walking down to them. And I'll be explicit because we're astronomers and we like quantitative things. There are 28 rows in this auditorium. So when I say front half, I mean 14 or lower. Okay. So we will have time for questions for all the talks. We are pressed for time, so please make sure your questions are sort of short to the point and questions. Also, please state your name so that people know who they're talking to. They might not be able to see you, also for the people online. We are monitoring the Zoom for questions from the online participants, and we'll do our best to relay those. Things that aren't answered, either in person or online, I encourage you to go to the Slack, and hopefully we can use that to follow up questions. There will be an SKA H1 Science Working Group breakout Thursday during lunch. You can find information about that posted in the Slack channel, and everyone is welcome to that, whether or not you're a working group member. It's an open meeting to encourage you to get involved and understand what we're doing. We have a lot of excellent posters, almost 100, so please check them out. We will have sparklers for a few, but just a few. We couldn't do that for all of them. I posted some information again in the Slack about how to find them. In general, the highest numbers in the exhibit hall are unassigned, and you can use them to sort of browse any poster. I think just to remind people, I don't think we really need this, but it's good to be explicit. Please be professional and respectful. This is the first or biggest meeting for many people here, so we just want everyone to have a really good experience. And so with that, I'll just say I'm looking forward to an excellent meeting, and I hope I'm well within time, so I've started us off on the right foot. So thank you.
Thank you, Betsy. Betsy is the chair of this whole symposium, so she's done a lot of work to put all this together. My name is Natasha Maddox, and I'll be chairing this session, the first session of neutral hydrogen in and around galaxies in the SKA era. And we'll start off with a review talk from Erwin de Block, talking about H1 in and around galaxies.
Great, thank you. Oh, sorry. Yeah, so resolved H1 studies of nearby galaxies was kind of the topic that I was asked to talk about. And of course, it's a very, very wide topic. This morning, we already heard a lot about, H1 in all its manifestations and various redshifts. And, there's a lot of history there, of course. I mean, we are now sort of almost 50 plus years away from the first resolved interferometric H1 maps that could actually map the H1 distribution in nearby galaxies in any detail. We about 15 years ago, had the Thing survey. I think a very revolutionary survey that really set the scene for a lot of the multi-wavelength surveys that we're seeing today. And of course, there are some new results that are coming out. The Mongoose survey amongst them. I'm not going to talk about this galaxy in detail, but please see these two posters that belong to this meeting. And so it's a really wide topic, and there's no real hope that I can cover this all in 25 minutes. So what I am really going to be talking about, rather than trying to give you a comprehensive review of everything that ever happened in the last 50 years, I will talk about targeted interferometric H1 emission surveys of field galaxies outside the local group. Very specific, but still, a lot to cover. I talked mostly about observations from the last 25 years or so. And what I will not do is give you a detailed, reference by reference overview of everything that was published in those over those years. But rather, I will use what I will introduce in a minute, a resolution column density diagram, and then introduce various surveys and kind of see how they fill in the diagram and what they have actually taught us about galaxy evolution, specifically H1 galaxy evolution. And then also at the end, kind of look forward to what is still there to be explored. How will telescopes like SK-MID and MEERKAT contribute to that? So if I kind of use the overview in Christie et al., the survey of surveys paper, and look at what would be the potential surveys for me to talk about, you end up with this list here. WISP, one of the very first ones, a lot of observations of nearby galaxies, all the way to recent surveys like FANGS that we heard a lot about last week. I will be talking about targeted surveys. I will not talk about all of these surveys. I will sort of take a selection of these, mainly the surveys which I am the most familiar. And I will also not be talking about the blind or untargeted surveys, such as Wallaby, operative, and also the Fornax survey. Wallaby Tobias will be introducing this after me, and later today, Filippo Mancagni will introduce the Meerkat Fornax survey. I will come back to them at the end once we have the context of all these surveys and also tell you where they are in this particular resolution column density space. So here is the diagram. We are seeing here on the horizontal axis the beam size, and on the vertical axis a column density sensitivity of each of the observations plotted here. These are all homogenized. These are all sort of taken from the literature and put, recalculated using the same definition. And you can see a lot of the surveys that I already mentioned this morning here, right? In the top, we see, the Thing survey, high resolution, moderate column density sensitivity, halo gases here. I'll come back to that. We see WISP up here. Just for fun, I also shown Wallaby here. And this really is the regime of very resolved interferometric observations. A lot of resolution, but not so much column density sensitivity. And that, of course, is the opposite when you go in the other part of the diagram, where the single dish observations live, where you have not so good resolution, but excellent column density sensitivity. And of course, the thing that we all want is in this particular diagram is that we want to push towards the lower left. We want high resolution, high column density sensitivity. So to make progress in this field, you really want to push to the lower left. And that, of course, is what we are doing at the moment with some of the Meerkat surveys. Mongoose is one of them, the Fornax survey. They are starting to explore regimes that have not been explored before. Now, some of you may think, why are all these points here, these old data points, and why are these surveys with Meerkat drawn as a line? Well, that is due to the specific design of the Meerkat telescope. If you look at the VLA, for example, a CRA, let's take that as an example, it has a very specific resolution where its sensitivity is optimal. As soon as you taper or smooth away from that optimal resolution, you lose sensitivity. And that, of course, is why the VLA has multiple arrays. And when you do a survey like Things, you take multiple arrays together in order to get a moderately flat noise distribution as a function of resolution. Meerkat has all of that built in. And so that's why, in this diagram, rather than data points, I'm showing them as a line. Now, you may think, well, this is a line. Why can't I take one of these old observations here and also smooth it? The line here is roughly 1 over beam size squared. So I take my Elvis data point here, I smooth the heck out of it, and eventually I reach the sensitivity from Parkes. Well, the problem is that there is such a thing as image fidelity. The number of baselines in your observation also counts. If you smooth far enough, at some stage you will run out of short baselines and you can smooth the heck you want. You will not get any signal because there is no signal in your data. We are starting to see this slightly already here in the Meerkat line at the lower resolutions. And if I were silly enough to really push this to the limit and really smooth the heck out of my Meerkat data, you can see we are bending away from the 1 over beam size squared. So this is something to keep in mind when you have your observation. It's not just the beam size, it's also the amount of information in the actual observation that you're trying to smooth. So we have talked about resolution in arcseconds so far. What we are really interested in, of course, is resolution in kiloparsecs. We want to look at physical scales. And for that, of course, we have to take all our galaxies, look up their distances, transform the angular resolution diagram into a physical resolution diagram. That's done in a nice paper which Filippo Mancagni mainly wrote about neutral atomic hydrogen surveys, past, present, future. I encourage you to take a look at this. I will be sort of describing these plots in a kind of hand-wavy style. The numbers are in the paper. So here's that plot. These are the same data that I showed you before, now shown as a function of kiloparsec. So you can see, Things, for example, high spatial resolution, also in kiloparsecs, not so good column density sensitivity, but as I will come back to, that was also part of the design of the survey. And here again, the single dish resolution of 10 to 100 kiloparsecs, but good sensitivity. Now that we have this diagram in kiloparsecs, we can of course ask ourselves, well, what do galaxies look like at any particular point in the diagram? And for that, I'm using a illustrious TNG simulation snapshot, just purely as an example. I'm not claiming that this is the one and all perfect view of a galaxy, but it's just to give you flavor for what information is retained as a function of resolution and column density. You can see this in this diagram here. Again, resolution here in kiloparsecs, column density sensitivity. And you really nicely see, in the various parts of the diagram. Here we have the Holy Grail, high resolution, high column density sensitivity, perfectly nice observation of the galaxy. At high resolution, but bad column density sensitivity, we are only seeing the inner star-forming disk. Here, it's really useless. And of course, here we still have a moderate column density, moderate resolution, but due to the high column density sensitivity, we are still picking up those filaments here. And so this kind of serves you as an example of what to expect when you look at galaxies in these diagrams. Here I'm showing them side by side. Once again, the VLA-like observations up here in the high resolution regime, single dish. And of course, you will see that there is a whole regime here that is not explored, corresponding to this part of the diagram. That's what we're trying to explore with Meerkat, for example, which SK Emit will explore, as I'll show in a minute. So let's now look at some of the surveys and put them in this diagram and see where they are. First one, WISP, one of the first large H1 surveys, about 200 nearby UGC galaxies at a reasonable resolution with Westerbork and a real focus on the dynamics of galaxies. WISP lives here. These points are all WISP points corresponding with this part of the diagram, where you can see you have a moderate resolution and a moderate column density sensitivity. So, WISP was not set out to map individual H1 clumps, nor was it set out to detect low density gas. But it really was set out to look at, the dynamics of a lot of these galaxies for the very first time. Rotation curves of dwarf galaxies, studies of the warps, and of course also one of the few surveys that really looked at that had made targeted observations of the H1 in early type disk galaxies. We have things, I already mentioned it, 30 odd galaxies, mostly late type. One of the first surveys, if not the first, that systematically used B-array data to get a high resolution, reasonable sensitivity, not so good, but enough to trace the entire star-forming disk. And it lives up here, like I already described. Things, but also little things, and relay angst to other surveys live up here as well. Very high resolution, really great for tracing the spiral disk. It focused on the relations with star formation, local dynamics, dynamics within the disk, rotation curves, and also one of the first to put a large emphasis on multi-wavelength. So in many senses, a precursor of the Funk survey that we now all know about. Overview of the H1 maps, a lot of detail in here. I won't go into detail, but you can see all the holes here in the disk. You can see the spiral arms, really a plethora of information here if you're interested in galaxy evolution. The multi-wavelength aspect, combination with Galax and Spitzer at the time really led us to get a good understanding of how the relation of star formation and gas density changes as a function of gas density or radius in the galaxy. Studies of dwarfs also showed that dwarfs are fundamentally different in terms of the H1 distribution, more dominated by the holes here caused by the stellar feedback, galactic fountain, things like that. And of course, one of the first surveys to have these really high resolution rotation curves, which helped us with addressing the cusp core problem. Adam Leroy also followed up on this by collecting lots of multi-wavelength data for the things and other galaxies, really starting off the whole multi-wavelength era that we have heard a lot about last week. Just some examples, the star formation law, the Kennedy-Schmidt law, as a function of gas density with and without H2, and your sort of classical papers that I encourage you to have a look at. Then there was little things, essentially the same as things, but looking at little galaxies. And here the emphasis was really on the dynamics of all these dwarf galaxies. Put them to scale, little things really is much littler than things. Core cusp issues, Seon did a nice study on the dwarf galaxies and definitively showed that, dark matter halos have cores and are not cuspy in these galaxies. Philae Angst, also a Things clone. So, Things was a very successful example, I think, of how to do a survey. And this really concentrated on the very nearby galaxies that had been observed with HST. And here the emphasis was, of course, on stellar populations and their link with the H1 distribution. I'll speed up a little. We have Elvis, about 80 nearby galaxies done with 3 compact array configurations. Elvis lives in this part of the diagram, sort of in the middle. So these observations are sort of good for getting a global picture of the galaxies, but they're not really focusing on any specific science angle in that regard. And then, of course, halo gas. This is the first survey that really started to go deeper in column density. The idea being that when you start looking at galaxies, in many cases the star formation rate is much higher than the implied gas accretion rate. So gas must be coming from somewhere. And then, of course, observations of galaxies like NG891, as they went deeper and deeper, showed more and more H1. So there was a good hope that we might find more of these examples of low column density halos around other galaxies. And that's what halo gas set out to do: 24 nearby galaxies, 120 hours with Westerbork, and really the first survey to routinely go down to 10 to the 19 or below in a resolved fashion. A new thing was also that galaxies, because of the high quality of the data, were individually modeled in 3D, so not just a velocity field and push a button, but really look at these things in detail and look at the specific structures of the disks. Halo gas lives down here. You can see it's at the lower part of where all the interferometric observations live. And really, you're starting to pick up little bits of this fuzz here, if it's really there, because of course this is just a model. Comparison with Things and halo gas at the same resolution, already showed there was a lot more in halo gas. But also this is an example where we got too excited because many of these galaxies actually did not show a lot of low column density gas. And that was really the galaxies that had, that's shown here, the implied accretion rate is only 1/10 of what you need to sustain the star formation rate. And that is really that we are finding that the galaxies where we saw lots of low column density gas were galaxies that were either interacting or that were had the galactic fountain processes sort of stirring, pumping a lot of gas out of the disk. So now here, what's happening here in this unexplored part of the diagram? We were hoping, of course, simulations were showing that as we go deeper, the 5 times 10 to the 19 sensitivity of halo gas, so taken from a simulation here, that if we were to go to 5 times 10 to the 17, that we would actually start picking up a lot of extra low column density gas. And so, halo gas was in a sense unlucky that it just detected the tip of the iceberg, but not really the intrinsic gas distribution. That led to Mongoose, which I will talk about in the next few minutes. Meerkat large survey project to use these very ultra deep H1 observations that we can make with Meerkat to really push that column density sensitivity down to 5 times 10 to the 17 or so in nearby galaxies. The survey is still on the way. We're almost done. You can already read the survey paper. You can go to the website. But really to show you, here's the line. The blue points are all the Mongoose galaxies for different resolutions. So, we are starting to cover this unexplored part of parameter space. Depending on our resolution, we really ought to be able to pick up all the low column density gas out here, even at a decent resolution. And of course, at the very highest resolution, we are just tracing the star forming disk, but at sub-kiloparsec resolution. The Mongoose galaxies, the sample deliberately chosen to have a large range in masses, just so that we can also trace different environments and sort of hope to describe accretion as a function of a host galaxy mass and, like I said, environment. Selected to be non-cluster and non-dense. We didn't want to sort of preferentially pick up, tidal effects and things like that. Philippe will in this afternoon talk about the Fornax survey, which is a really different environment where we are seeing galaxies behave really differently So in that sense, these surveys are very complementary to each other. The galaxies to scale, from really tiny dwarfs to really large spiral disks. Just to give you an idea, one of the first high-resolution observations that we made of one of the Mongoose galaxies, fantastic detail in the spiral arms, streamers. We can see the outer disk being disturbed there. If you look at the low column density gas, this is a 3 times 10 to the 17 contour, so unprecedentedly deep. We really are starting to see that the outer disk is really, really ratty and has all sorts of structures, hints of an interaction with this galaxy here, AGC 1581. And also here a tiny galaxy, which was already mentioned this morning. One of the lowest H1 mass detections outside the local group, a little dwarf galaxy, H1 mass of 10 to the 6 or so. It seems to have a hint of rotation, but it's very likely that it's on this first infall and will be stripped in a few mega years. So we're really lucky to catch this at its current stage. But this is local group science at 20 megaparsecs. So that's the great thing that Mongoose can do as well. And that's all I'll say about it. You've already seen 5068, which is a really interesting galaxy, which seems to have an inner undisturbed disk, an outer diffuse disk-like component with a different orientation, as you can see here from the velocity field. We are seeing high velocity dispersion, where these two components kind of interact, not caused by an intrinsically high dispersion, but by multiple components along the line of sight, which tells us that this is not yet stabilized, and most likely we are looking at a warp information. But of course, the big question here is, where does this gas come from? It's too much to be solely due to a dwarf being disrupted. We also do not see any evidence in the optical, very deep observations of any additional stellar components out here. So this is still an intriguing galaxy that we will keep looking at. Another, we are seeing interactions, but not the interactions that this morning you saw M81 in the plenary. You may think, well, this is just also an M81-like thing. Well, no. If you were to make a map of this at the M81 resolution, at the M81 column density sensitivity, you would just see 3 boring galaxies that had nothing to do with each other. This interacting stuff is all happening at 10 to the 18. So this also is the first time that we are seeing, these things happening at very low column densities, but having no effect on sort of the inner disks of the main galaxies. And Dane has a poster on that. I encourage you to look at. Just as the talk by Sushma, 2 talks after me, who will tell you more about this intriguing system with all these sort of 11 dwarfs that we are seeing here. No dark galaxies here. These all have stellar components, even though they have 10 to the 6, 10 to the 7 solar masses only. I don't want to give you the impression that all these galaxies are as exciting as 1566. This is a busy environment, but we also see galaxies like this. And you see J2257 minus 41, and you see 7424, where you see this really steep drop in column density from almost 10 to the 19 to 5 times 10 to the 17 within one beam. That's within 1 kiloparsec, a really, really steep edge of a disk. And it's surprising that in our sample we are seeing such a large variety in sort of the shapes and the drop-offs that in the outer parts of galaxies. Very quickly now, simulations, we heard a bit about that as well. Ramesh published a detailed study of Milky Way-like galaxies from the TNG50 simulation. We figured out, well, we have Mongoose galaxies that obey his selection criteria. So what we can do is we can take his simulations and we observe them. We push them through the Meerkat pipeline, and this is what these TNG galaxies look like after 55 hours observation with Meerkat. Lots of fuzz around it that we don't necessarily see in the observations. Very different column density distributions. Green is the Meerkat data. Red and orange are the TNG and fire simulations. And also very different velocity dispersions. Very high velocity dispersion tail, up to 120 kilometers per second or so, that we are seeing in the simulations that we're not seeing in the observations. And remember, these are one-to-one comparisons, right? These are mapped at the same resolution, etc. So this is a direct comparison that we are making. You can divide the observed simulations in 2 subsamples. One with a lot of fuzzes around it, so where more than half the area covered by H1 is outside the main disk, and one which have a very small covering factor, which are these galaxies, and that's also where the observed Mongoose galaxies live. So not a lot of H1 out there compared to the simulations. You can see that in the histogram here. But the strange thing is that you think, okay, well, that means that these simulations, lots of fluff, probably have lots of satellites near them. They disturb stuff. And, you know, the mongoose galaxies are just the ones that happen to be in a quiet environment. And that's why we're not seeing any further gas. But the opposite is true. The mongoose galaxies, the observed galaxies, actually have more satellites than the simulations. So, you know, if anything, the mongoose galaxy should be disturbed. They should have all this fuzz floating around. So that's an interesting paradox that we have yet to solve. So I've given you all this information already. So let me just in my last minute tell you a little bit about the future. Again, I promised I would come back to Wallaby and also Aperitif and Meerkat Fornax survey and see where they are in perimeter space. Well, you can see this sort of half open rectangle is the Wallaby survey. It will really clean up the upper part of this diagram. That's really, really good. Up to, you know, things like resolutions, things like sensitivity. Aperitif, similar story, roughly also in the Wallaby parameter space. And of course, Fornax was sort of created to have the same observing strategy as mongoose. So it's very, very near where mongoose is, and also is starting to clean up what's happening in these low column density areas. The area axis, though, is missing. You know, this, of course, is an almost the southern sky. This is a significant part of the northern sky, done with Aperitif. And of course, that's not something that is not reflected in this diagram, where, of course, I'm only showing targeted observations. So that's one thing, of course, to keep in mind. The payback of these untargeted surveys is potentially also much larger than this diagram suggests. The future, DSA 2000, if it happens, we'll do things all sky at 3 arcsecond. No need to ever observe the northern sky in H1 again. Fantastic. SK1 mid, 10 hours with SK1 mid will already surpass mongoose. So that opens really options for doing mongoose-like studies over samples that are, you know, hundreds of galaxies rather than just 30. 100 hours with SK mid, you go 10 times deeper than mongoose. You really are pushing the 10 to the 16 regime there. So you're starting to marry together the absorption and the emission regimes in a very direct way there. I have not mentioned fast at all, but of course fast down here in this low column density regime will also help us, you know, constraining the presence of that low column density gas. So it's an exciting time. We are already being deluged in data. We're going to be deluged in more data, but at least we will use that to give a complete characterization of galaxy H1 properties. And in that sense, I think the next 5 to 10 years will be extremely exciting in H1 land. So thank you.
Thank you, Erwin, for staying to time and a beautiful talk. Are there questions in the audience? There's someone just over there. Yeah. And remember to say your name so that we all know who you are.
Thank you very much. I'm Céline Perroux from ISO in Germany. I wanted to come back to the comparison with TNG 50, which of course doesn't have H1 per se, but I guess is post-process, right, to get the split between H1 and H2. And then also, you know, you were mentioning the lack of satellites, but again, there is a mass limit in TNG 50 of about 10 to the 8th stellar masses. So I was curious how this limitation in the simulation may affect the results that you were presenting here in your view?
In terms of the mass limit for the satellites, yeah, we specifically took that into account. So, you know, we only took the massive galaxies in our we only counted the massive galaxies in our observations because we knew that 10 to the 6 is not the regime where you want to be comparing. So that's one thing. The H1, you're completely right. There are recipes that kind of paint the H1 almost. We have chosen the recipe that best describes the observed H1, H2 fraction in observed galaxies. There are other, so it's there are other recipes, more recent recipes that I think give a much higher H2 fraction compared to the H1 fraction, and they would really only strengthen the discrepancy of what I've shown. So this really is the case that best compares with the simulations.
I'm Federico Lelli from INA Florence. Thank you, Erwin, for the very nice overview. So I also have a question regarding the comparison between mongoose and TNG at low column densities. So do you think there is a way to tell whether this is a problem in the gas physics, so the recipes that you just described, or whether it could be a problem of the underlying cosmological model, in the sense that there are so many entirely dark subhalos that are messing up the H1 distribution in the other parts too much?
My feeling is it's the former, that it's really to do with I think the simulations in that sense are too energetic. There's too much stuff happening. We thought when we were going to do the comparison that we would be sort of struggling to compare things to 10 to the 17, and you say, oh, there's 5% more and 5% less. These discrepancies that I'm showing are happening at 10 to the 19. So it's really up there. It's halo gas already showed this result. Except, it was close to their sensitivity limits. But with hindsight, they already showed that there's not a lot of H1 out there. And it's also dispersions. We are seeing, these filaments are coming in. They are crashing into the disk. They cause hotspots of 100 to 20 kilometer per second dispersion in the outer parts of galaxies, which we don't see. So I think it's really, accretion is a lot more gentle than simulation suggests, I think would be my summary.
Hi, Erwin. Luca Cortese from Perth. Very nice talk. So I wonder, you cover a wide range of stellar masses. And from a theoretical point of view, the expectation would be that the local universe, it's much more likely to see accretion via filaments in dwarfs. So I wonder whether do you see any mass effect on the likelihood or the presence of low column density H1?
We're seeing a mass effect in the sense that around dwarf galaxies, things are a lot more quiet. Whenever we see these structures like around 1566, that's in the more massive part of our sample. And I think that's just because, when you're a large galaxy, you're more likely to have smaller galaxies around you. Because that's the other thing, we only see the low column density H1 in galaxies where stuff is happening. But one example that I showed, 7424 with a really steep disk, it has no satellites, nothing. So I really think there's an environmental effect that really determines what we are seeing.
Okay, and with that, we've run out of time for questions. So let's thank Erwin again.
Yep.
And we'll move on to our next speaker, which is Tobias Westmeyer. So if you can come up here, talking about the first public data release from Wallaby.
All right, thank you very much. I hope you can hear me all right. Thanks to the organizers for giving me the opportunity to talk to you today about Wallaby and to give you a bit of an update and in particular highlight our first public data release. To start with, just a quick overview of Wallaby. Wallaby is the all-sky blind H1 survey with the Australian Square Kilometre Array Pathfinder, led by Barbara Catinella and Lister Stavely-Smith. Wallaby will cover a sky area of approximately 14,000 square degrees across mostly the southern sky, out to a redshift of about 0.1 at an angular resolution of 30 arcseconds and a velocity resolution of approximately 4 kilometers per second. So unlike mongoose, Wallaby will be a wide but shallow survey. And you can see a map of the sky coverage here. So as you can see, we're covering a continuous declination band from about -15 to just below -60 degrees in declination. And then on top of that, we have a few individual fields of interest in areas where we have a lot of multi-wavelength coverage. In particular, we've got these two equatorial stripes in the direction of the hyper-suprime cam SSP regions. We'll also be covering the Virgo cluster region over here and the Gamma GO2 region over there. The full Wallaby survey is currently underway, and once completed, we're expecting to detect about 200,000 galaxies in the 21 centimeter line of H1. Before we started with full survey observations, we did carry out a pilot survey, and that was done in two phases. Phase 1 is shown here in blue, and phase 2 in red in this map. In total, we covered 6 regions of interest, mostly in the direction of nearby group and cluster environments, with a total sky coverage of 360 square degrees. And these observations were quite successful. So we picked up almost 2,400 galaxies in the pilot survey alone. And just as a comparison, that's about half the sample size of HiPass just in the Wallaby pilot survey. And we also use the full ESCAP array. So we've got the full Wallaby sensitivity and resolution for the pilot data. And here is just an example of what the data actually look like. So this is a large region of the sky. This is about 15 degrees across in the direction of the NGC 5044 group. And you can see literally hundreds and hundreds of galaxies. So we picked up, I think, more than 1,300 galaxies just in that field alone. And you really need to zoom in to start to see all of the glorious detail of these images. And just as a reminder, this is not a radio continuum image of the sky. This is an H1 moment zero map coming from the SOFIA source finding pipeline. And if I zoom in even further, you can see the full resolution and detail of the data. And so what makes Wallaby unique is the fact that we're combining huge samples of galaxies with a sufficiently high angular resolution to resolve a significant fraction of those galaxies. And that opens up a lot of new interesting science. And the Wallaby team has, in fact, been busy writing papers already. So we've got 24 science papers to date. That includes both early science and pilot data. And that covers topics such as H1 scaling relations, gas stripping in groups and clusters, the Tully-Fisher relation, dark galaxies, ultra-diffuse galaxies, polar ring galaxies, you name it, and even things that we didn't originally envisage, such as the discovery of a fast radio burst in one of the Wallaby observations and the subsequent detection of an H1 component to the FRB host galaxy by Glowatsky et al. in 2003. So there's a lot of interesting science, expected and unexpected science to be done. And I would like to focus on just two science cases, which in my opinion showcase this combination of large sample sizes and high angular resolution to really do some exciting science. One of those is polar ring galaxies. This is work done by my colleague Nathan Degg, who discovered two polar ring galaxy candidates in our pilot data. One of these two cases is shown here. And he was able to separate the main body from the anomalous gas in the ring in each of those components. Unfortunately, you can't really see the low column density stuff very well in this image here. But what he found is that about 50% of the gas is actually located in the anomalous ring, which is quite a lot. And what is even more interesting, he was able to estimate that the incident rate of polar ring galaxies in the sky should be of the order of 1 to 3%, which is much higher than people had previously thought. And the reason simply is that we didn't have the resolution in the past combined with the large sample size to simply detect these things in large numbers. But Wallaby has the potential to detect hundreds of these polar ring galaxies, and that will allow us to study them in much greater detail and try to investigate what their origin is and their physical properties. Another interesting topic is resolved galaxy H1 scaling relations. So this is work carried out by Sona Lee, who is a PhD student of Barbara Catinella's and myself at UWA. And so if we look at H1 scaling relations, such as the gas mass fraction as a function of stellar parameters, such as stellar mass, or in this case, stellar mass surface density, we have these nice linear relations, but there is also an awful lot of scatter on these relations. And the question is whether part of that scatter could come from the fact that the H1 disk is typically much more extended compared to the stellar disk. And so we're including gas that does not actually contribute to star formation in the disk. So with Wallaby, we now have not just the large sample sizes, but we also have the spatial resolution to directly measure the H1 mass within the stellar disk and do the scaling relations to see if that reduces the scatter. And here's some preliminary work that Sona has been doing. So in the top plot, you can see the H1 gas fraction versus stellar mass surface density, including the entire gas component. And you can see the scatter here is approximately 0.3 dects. But when she includes just the H1 within R25, the optical radius, then you can see we get the same kind of relation. The slope doesn't change, but the scatter drastically reduces to 0.2. So that's some very interesting results, and Sona is currently in the process of writing up a paper to highlight all of these results. Lastly, I'd like to use the opportunity to advertise our data releases. So all of the Wallaby data will be made publicly available. And we have already released all of the data from phase 1 of the pilot survey. So that includes roughly 600 H1 detections. And in addition to that, just over 100 kinematic models of galaxies that are sufficiently spatially resolved to do the modeling. That was all released back in November 2022. And there are 2 data release papers which describe both the source extraction as well as the kinematic modeling in great detail. And I was hoping that by the time I give this talk today, we'd have the phase 2 data released as well. Unfortunately, we have had a few delays with that. But it's now really just a matter of a few weeks. So the data release is imminent. So stay tuned. And that will give you access to another 1,300 H1 detections from phase 2 of the pilot survey, plus another 120 odd kinematic models. And for the first time, we will also release 80 high-resolution cutouts of all of the high-pass galaxies in the phase 2 pilot fields. And so that will come with 12 arc-second resolution, so even higher resolution, but only for a small sample of galaxies. And just a quick overview of the kind of data products that you can obtain. So we're doing our source finding using the Sophia source finding pipeline, which is publicly available on GitLab. And so you'll have access to the full source catalog with all of the source parameters. In addition, you get all of the individual data products for each detection that Sophia produces. So that includes moment maps, spectra, little cubelets with masks and so forth. In addition, the Wallaby Kinematic Working Group has also been working on doing the kinematic modeling of galaxies that are sufficiently well spatially resolved, as I mentioned earlier. And so that gives you access to things such as rotation curves, H1 mass surface density profiles, model cubes of the modeled galaxies, which are shown here as the pink contours on top of the actual data, and so forth. And in fact, the Kinematic Working Group has now developed its own kinematic modeling pipeline, which is called Echidnas. And again, you can download that from GitHub and use it on your own data if you like. Just a word of caution, given that this is pilot data, there are still a few teething issues that we've had to deal with. That includes things such as bright continuum residuals that are affecting some of the pilot data. We've had some issues with RFI from the on-dish calibrators on ASCAP. We've had some uncertainty about the primary beam model, which has now been fixed. Some residual side lobes in some of the data cubes. And we've also had some issues with flux uncertainties, which are related to the fact that in particular, the very faint galaxies are only partially deconvolved, and that leads to some uncertainty about the fluxes. So please bear these things in mind if you're planning to use the data, and in particular, have a look at the data release paper, which has all of the details of those caveats. And there are some information about how to mitigate against these problems as well. And a lot of these things have now been addressed. And so the phase 2 data are a lot cleaner already than the phase 1 data. Hence, we have also more detections in phase 2 compared to phase 1. So lastly, how do you get access to the data? So we've got copies in 2 places. The first one is the Canadian Astronomy Data Centre, or CADC in Canada. The second one is the CSIRO ASCAP Science Data Archive, or CASDA, in Australia. So we've got identical copies of all of the data products in these 2 data centers. It doesn't matter which one you go to. And there are 2 ways to access the data. Either you can directly navigate in your browser to the CADC or the CASDA website and just search for Wallaby data and download catalogs and images straight to your computer. Alternatively, we also, both CASDA and CADC have a tab server. And so you can directly access the catalogs through any VO-compliant software such as TopCat, or here is just an example of how to use Python to extract, in this case, the Wallaby DR1 source catalog from the CADC tab server. And so literally, there is just 3 lines of Python code in between you and the data. And I'd refer you to our website, wallabysurvey.org/data, for all of the details. And every talk obviously needs to have a QR code. So here is mine, and that'll get you straight to the data download page where you can have all of the information on how to access data. And on that note, I'd like to end. Thank you very much.
Thank you, Tobias. It's beautiful data. Are there, hold on, any questions? We'll start over there. Yeah, go ahead.
Yeah, hi, IAU GA from Max Planck Institute for Radio Astronomy. Thanks a lot for the beautiful talk. With respect to the polar ring galaxies, you said, or you claimed that the mass sensitivity is the parameter that made that brought up the detection rate. I'm wondering if this is particularly true because see the Whitmore sample and Whitmore did the first survey of this that was based mainly on optical data and dust lanes crossing the disks. Well, this is actually, I think, the first time that really a massive number of galaxies have been looked at and sought for in the H1 component. So I think this is a different class of objects even that we are looking at.
Yeah, that could potentially be true. It's not the mass sensitivity, but it's the combination of angular resolution and large sample size that allows us to detect these things. And even at the resolution of Wallaby, there are still a lot of galaxies that are only marginally resolved. So you could still hide a lot of potential ring galaxies because the resolution is not sufficient to actually detect them. And I think that was also part of Nathan's estimate of the incidence rate.
Hi, Tobias. Enrico Di Teodoro from the University of Florence. Thank you very much for the very nice review. So my question is, so given all the problems that ASCAP is showing and the computational center is showing, so how confident are you that this survey will be completed with the initial numbers and in a reasonable time scale?
Yeah, I mean, I can't foresee the future, obviously. Progress has been slow, but we're still hoping that we'll be able to make more progress over the next few years. So it's impossible for me to tell at this point in time, but we're still confident, let's put it this way, that the survey speed will pick up and we'll be able to finish the survey, perhaps not within the first 5 years, but with a few additional years added on top, that might be possible.
Okay, thank you very much. We've run out of time for questions, so let's thank Tobias again. And next up we have Sushma, and she's going to talk about uncovering extraplanar gas with mongoose.
Yeah, so I'm going to talk about the extraplanar and anomalous gas. In UGCA 250, this galaxy was observed as part of the Mongoose survey. And on the left, you can see the optical image of this galaxy, which looks like an edge-on galaxy. And on the right, you can see the H1 moment zero map. And you can clearly see that there is a lot of gas in the vertical direction. And so here we will try and understand what could be the origin for this extraplanar gas. So first I'll show some interesting features of this galaxy and present some of the results from detailed kinematic modeling of this galaxy. And then we can discuss what could be the origin for extraplanar and anomalous gas. So Erwin had given a very nice overview of gas accretion and column density sensitivities and resolutions, etc. So we know that gas accretion is necessary in order to sustain the observed star formation rates in galaxies. And this gas accretion can occur through various mechanisms, for example, through a galactic fountain flow model. So in this model, supernovae explosions expel hot hydrogen gas into the halo of the galaxy, and which then cools down and condenses before returning back onto the disk. And this gas accretion can also have other external origins. For example, like the gas could be brought onto the halo by satellite galaxies, or there could be fresh gas accretion from cosmic web. And so And so halo of the galaxy forms its connection with the intergalactic medium. And in order to understand these various gas exchange processes between the galaxy disk and the circumgalactic medium, it is important to study this disk halo interface region of the galaxies. And as Erwin mentioned, this work has been done by halo gas, and this is the very famous example of NGC 891, and we can clearly see that at column density of 10 to the power 20, it looks like this. And at column density 10 to the power 19, we can clearly see a lot more gas, and the gas extending vertically out to 14 kiloparsec. So basically, deep H1 observations have shown the presence of extraplanar gas in some of the nearby spiral galaxies. And one powerful method to understand the origin of the extraplanar gas is actually to study the kinematics of this extraplanar gas. And as shown by Erwin just now, Mongoose is an ideal survey for such studies because it actually provides us with a unique combination of very good column density sensitivity in combination with high resolution. So that is actually perfect for doing such studies. And this is the galaxy of our interest. As you can see on the galaxy image on the top right here, we can see that it looks actually like an edge-on galaxy. And as we go deep in the optical, we can, on the left, you can see the deep optical image from the Vega survey with VST. We can see that at brighter magnitudes, it looks like a thin and elongated structure, whereas at fainter magnitudes, we definitely see more vertical extension. And also the stellar distribution actually looks asymmetric. There is some extension towards the southwestern region, and we can clearly see this break kind of a thing in all the images actually. So clearly something is happening even in the optical images. So this is how it looks in H1. So because of the amazing field of view that we have with meerkats, and in combination with very good column density sensitivity, we have actually detected around 9 companion galaxies. All of these are actually dwarf galaxies. A lot of them are in between 10 to the power 6 to 10 to the power 7 solar masses. And in the field of view, there is also an elliptical galaxy, which is at the same redshift as that of this UGCA 250, with a projected distance of 200 kiloparsec. However, we haven't detected any H1 in this, with a H1 mass upper limit of 10 to the power 6 solar masses. And in order to check whether we detect any intra-group gas, we have overlaid the low column density gas from low resolutions, and we can see that there are hints of intra-group gas, and we also see this tail kind of features in some of these companion galaxies. Yeah, and so there is more gas around galaxies here. And now, if we look at the UGCA 250 at high resolution, we see that there is a filament, and then there is a blob which is just situated below this filament. And clearly there is also a warp, and this red contour represents 10 to the power 20. And as we go into more and more low column density gas, the warp also becomes more prominent. And as we transition into lower column density sensitivities, it's interesting to note that the disk, the radius of the disk doesn't increase much, whereas it grows substantially in the vertical direction. So here are some moment maps. So this filament actually extends out to 40 kiloparsec. And this is the moment 1 map. And we can see that there is a cloud which is at different velocities compared to the galaxy velocity. So the cloud is at a forbidden velocity, and we can see this more clearly even in moment 2 map, where it shows very high values for the moment 2. And this is not because of the velocity dispersion itself, but because the cloud actually is at a different velocity compared to the galaxy. However, there is another high velocity dispersion region in the top, and because this cloud was situated at a different velocity, we could actually separate it. and these are the moment maps of the cloud. So there is some hint for velocity continuity here. However, we haven't seen any optical counterpart for this cloud. Now, in order to understand the vertical structure of this galaxy and to specifically understand whether whether the gas has truly anomalous kinematics or if it is produced because of projection effects or disk thickness, we developed several models, and we then compare the models with the observed data cubes. And so we developed the models using terrific software, assuming a standard tilted ring model, where we assume that gas disk is a set of concentric rings, each characterized by their own parameters like position, angle, and inclination, etc. So here we consider three scenarios. One is that the gas disk is in form of a single thin disk with a single scale height, and the second scenario is a flare, where we assume that there is only one component, but the scale height is varying as a function of radius, which is also called as the flare. And the third case is that there are two components. One is a thin disk with a smaller scale height, and the other is a thick disk or halo with a larger scale height. So we consider these three scenarios, and we find that this galaxy actually has a warp in both positional angle as well as inclination angle, so which change with radius. And so this is a PV diagram across the major axis, and the rotation curve is overlaid on it. Now, in order to compare various models, we actually use PV diagrams across minor axis and PV diagrams across axis parallel to the minor axis, as well as channel maps. So here I'm just showing the PV minor axis diagrams. The left column shows data, and the second column shows thin disk, and the third column shows flare, which is scale height varying as function of radius. And in the fourth column, there are two components, one thin disk and halo. So clearly, thin disk is not a good representation of the data, and even flare is not an accurate description of data, because we can see in channel maps also more clearly that the halo is actually a better two-component model is a better description of the data. We have also done some more modeling, which I'm not getting into here. But the main conclusions of the modeling is that we found that the thick disk or halo has a scale height of approximately 3 kiloparsec, with 15% of the total H1 content residing in the thick disk or halo. And clearly we see a warp, which is very pronounced, which is also seen in the moment zero map, but we also find it in our modeling. And we also find that the halo gas is actually rotating slightly slower compared to the thin disk, especially in the central regions, which is also called as the lag. And we also found some evidence for radial motions especially in the outskirts of the galaxy, on one half of the galaxy. So this could have been triggered by potential tidal interactions, because we also have other evidence for tidal interactions, because we see a lot of companions as well as intragroup gas, and even the optical image of the galaxy shows asymmetries, etc. Now, even after so much modeling, there is a lot of gas left out, which is, there is gas left out which has not been modeled. So these maps are the moment 0 and moment 1 of the gas that is not modeled. And so the unmodeled gas is around 10 to the power 7.7 solar mass, about 0.7% of the total mass of the galaxy. So all these features like blob, filament, cloud, and the high velocity dispersion region were not modeled. So to summarize, this system is probably in a group, because there is also an elliptical galaxy which is not detected in H1, and it has around 9 dwarf galaxies as companions. We see various features like a filament extending out to 40 kiloparsec, and there is a high velocity dispersion region, and there is also a cloud at forbidden velocities, which seems to show some continuation. Maybe it's a galaxy, but we did not see any optical counterpart for that. And we construct a detailed tilted ring model in order to understand the vertical structure. And we find that a thick disk with a scale height of 3 kiloparsec gives the best fit. And finally, probably it has a mixed origin for the extraplanar gas, where there is probably both internal processes and external processes, like tidal interactions with satellites are also playing a role. Thank you.
Thank you, Sushma. That's beautiful work. Are there questions in the audience? There's just back there. Yeah.
Thank you very much. Excellent. So I'm Céline Pirou from the European Southern Observatory in Germany. I wanted to ask you, and maybe other speakers as well, have you plotted the H1 column density distribution of these objects? See how many H1 column you get as a function of column density?
How many detections we get as function of column density, you mean?
Exactly.
Yeah, so actually sorry. So among the 9 satellite galaxies, so this is 55 hours data with Meerkat. So we are reaching around, whereas in the single track observations with 5.5 hours, only 6 or 7 of them are detected. So we found 2 or 3 new detections with 55 hours with Meerkat. I don't have the plot exactly, but yeah.
Okay.
We did detect more with the ultra deep observations.
Okay, thank you.
Yeah, Robert Braun, SK Observatory. Well, thanks for a great talk. One thing that comes to mind just from the environmental overview that you showed us with the elliptical there in particular, is that ram pressure within that environment for an infalling system, if that's what's happening, seems like quite a plausible scenario for a lot of what's happening in terms of driving a warp, driving indeed gas loss. Have you explored that scenario at all?
No, not yet.
So we've run out of time for questions for Sushma, so let's thank her again. And next up, we have Moses Magotsi talking about Mir choirs, which is H1 in nearby galaxy groups. So your microphone's not on, I don't think.
Testing. Okay, can you
Now
hear
it
me
is.
now?
Yeah.
Oh, you missed my whole bit about interpretive dance. Oh well, too bad. Anyway, so the interpretive dance that I was going to do was going to be about looking at galaxies and galaxy groups. Now we've heard a lot of interesting talks this morning, mostly about sort of individual galaxies and their kinematics and sort of their role in our understanding of how galaxies evolve. So a lot of the galaxies that were shown were actually in groups, and I would like to point out that. For me, groups, the importance of groups was really, really highlighted to me whenever I see this particular image over here, where if we look at this particular group in the optical, we just see 3 happy little galaxies in each other, each with interesting properties. But then when you see the H1 in these galaxies, you see a whole different picture. And this is sort of what attracted me to studying groups of galaxies, because in H1, especially because with the H1, you can really, really then see all the different kinds of interactions in these groups and sort of really get a better idea of like how the galaxies get their gas, where this gas is going to go if the galaxies lose their gas, and how all of this affects the evolution of galaxies. Because as I think we've been seeing, in a lot of cases, we need to consider the environment if we want to understand the evolution of galaxies. Now, people know about clusters, but I think I want to highlight how groups are such an important aspect of this because most of the galaxies we see are in groups, and these groups are a nice intermediate stage between sort of low density environments and the dense clusters that can have much more extreme effects. And actually, even in those groups, you can have extreme effects. And highlighted by this is the images shown on the whatever this hand is, the left hand showing the HCGs, which are Higgs and compact groups, and showing the different phases at which these groups can exist in. And these are very compact groups. So you can see extreme evolution of galaxies and their gas, even in very, very dense, sort of in dense systems, even in group environments, or like one of our Meerkwijs groups, 1059, you can see sort of very relatively looking relaxed galaxies sitting by themselves, not necessarily in extreme interactions like this. So how does all of this affect the evolution of the galaxies? And also what is going on about what is the gas doing in these galaxies? As you can see in the HCGs, you can have extreme effects that remove most of the cold gas in the groups. So what about other kinds of groups? So this was also sort of inspired by a previous survey that I was working on, which is the SING survey, which is a high-pass-based survey where they identified some high-pass galaxies and then did the optical follow-up of those galaxies. Now, in those follow-ups, they found that some of these galaxies were in groups. And in these groups, they were quite an interesting set of groups because they're H1 selected groups, so they're groups with star-forming galaxies in them, and they're quite nearby. And this became a great laboratory, for me at least, for trying to study groups. And as I said, the H1 based sample, which means that these are star-forming galaxies, and they also have emission lines as well that we can see. And there are no bright ellipticals in these groups. That's another important point. So this is a different sort of type of group than maybe some other groups that might be much more extended and much more evolved or have elliptical galaxies in them. So another thing, this I think highlights that point when you look at the H1 deficiency, that a lot of the groups are H1 rich, and very few of them are H1 deficient. So that's an important note to mention as well. And we can see a nice comparison here between them and the HCG galaxies, whereby they tend to be, if you compare them to Higgs and compact groups, they tend to be sort of on the not as evolved, for lack of a better word, scale of that, and more extended than those groups. Yeah, so this led to this Meerkwijs survey, which is a survey of these nearby quiet groups using Meerkat to study the H1 in these groups. And we're trying to answer a whole bunch of questions with that. And hopefully some of these you'll see why or how we're trying to address those questions, and also why we use Meerkat to perform the study. So one of the things that I think initially attracted me to this was that when you looked at the H1 data of these groups before, it looked something more like this. So this is, I think, ATCA data of one of the galaxy groups, and this is by Robert Cesar, one of the members of the collaboration. And you can see that one of the problems you'll have is that if you don't have great resolution, you can't tell much about what's going on, let's say, in the dwarf galaxies, or even study the interaction in detail. And so compare this to Meerkat, where now with better resolution, we're able to actually identify dwarf galaxies and study the interaction between the galaxies in much better detail, which is one of the key components if you want to understand what's going on in these groups. And so instead of sort of not being sure how these two sort of sets of galaxies are connected, we now have a clearer picture of what's going on. And we couldn't resolve the individual dwarf galaxies, but now we can in this image here, which is the one at the top showing the sort of nicely resolved image of the galaxies in J1250. And the other thing that's, I think, important to note here is we also get a much bigger field of view than other typical previous H1 instruments. So we can then look at a wide area around that group. So high-pass beam was about 15 arc minutes. So we selected groups that had at least four members within that 15 arc minutes. But now with Meerkat, we can look at the entire region and study the H1 and see whether there are other group members, whether there's other structures surrounding these groups, and study all of that and the H1 in there to understand how all of these are affected by the environment that they're in. Like this is a nice example where we then see that instead of the galaxies in the middle, this whole group has other sort of galaxies nearby and other substructure as well that will affect what's going on here. And then the other thing is we can get different kinds of interactions in the group. So this is some of the work that one of my students, JC Phil is working on. And you can see that you can get in the same group multiple kinds of interactions as well, in that these two panels over here are two sets of like galaxies all within the same group, or at least two subgroups in the same area. Another thing is we can also study the galaxies in detail. Not only can we resolve them like in resolve dwarf galaxies, but we can study the bigger galaxies in a lot of detail to do a lot of complex analysis. And when you do study these galaxies, you see a lot of interesting sort of effects, such as those two galaxies. Now you see there's whole big tails connected to the two galaxies, and you can see that the interaction between them is much more complicated than you would have thought otherwise before. And this is all the information that a telescope like Meerkat can allow you to do, and allow you to really study the groups in a lot of detail and better than we could before. And in conjunction with this, I'd like to highlight our sort of what I like to call our sister survey, which is led by Lourdes and the team at IAA, where they're looking at our Higgs and compact groups with Meerkat as well. So they're basically doing what we're doing, but doing it for those Higgs and compact groups. And in those, since they're much more dense, you have much stronger and more intense interactions, leaving you where you have systems that are sort of in the maybe earlier phases that still have a lot of H1 gas in the galaxies, but a lot in between, and into stages where the system evolves further, and you have very little gas sitting in the middle of these galaxies. So I'd really advise you to go see, I think Yanja has a poster up this week, I think tomorrow. So I'd really advise you to see that and to look at some of their work. So it's quite interesting. So in our groups, though, we have a lot of gas, and usually there's a lot of gas on the galaxies, and there's seemingly a lot of gas outside of the galaxies. And one nice example is this one from JC's work, where we're seeing this interesting interaction in the middle of the group. And when you look at it, you see this massive H1 structure connecting all of these galaxies, where what we're now trying to do is understand where the gas is. Is the gas still left in the galaxies? How much is outside of the galaxies? How much is between the galaxies? And what is the fate of all of that gas? And we're then trying to isolate and determine what's happening in these structures like this, and then what is the fate of the gas in such structures, which is quite interesting. And then we can also do this and find interesting objects in these groups as well, like this, what I like to call a nice big super disk, 150 kiloparsec diameter sized disk in this galaxy that includes a little friendly little dwarf that we can now try and study. And as I said, you can now separate out individual galaxies like that one and that one in the H1 to study how they're all interacting with each other, or at least try to do that. And if there's an embedded dwarf like here, the nice thing about this is we've got the velocity resolution and the resolution to at least try and tease out how a galaxy like this and its little friend over there are interacting, and how does that affect the larger H1 disk. And maybe we'll see more of these giant disks around everywhere. And the other thing you can see is weird instances like this, where we see this a dwarf galaxy in the middle there nearby a larger galaxy, and this sort of tail of gas connecting them that consists of about 25% of the gas relative to the dwarf galaxy. 25% of the gas mass is in this little train of gas that's either leaving or going towards that other galaxy. So in another case, we can try and study this in detail and understand where that gas is going, where it comes from, and what's happening with it, and instances like that. And the other thing we can do is the complex modeling of the galaxies in these groups. And this is, I think, a very nice poster child for that work done by Suram, where we have ARP271 and these two galaxies. And with the data, we can sort of try to model the galaxies, and a key part of this is separate them out, trying to identify what gas belongs where, separate that out, and then how much of in that system the gas is left in the disk is extraplanar and is extended gas. And this is some of the work that he's done using Gaussian decomposition through Gauss-Pike, Bayes-Goud, along with modeling software such as 3D Barolo, to be able to look at this sort of look at this H1 distribution and determine what part of that is from that galaxy and what part of it is from there. Whereas in optical, you can't really tell. And this then leads us to interesting results such as this, where in this system, Suram was able to determine how much mass is in these tails, and also how much mass is extraplanar in each disk, and how much mass is left onto each disk. And this is quite important because this helps us understand better what's going to happen with the two galaxies and what an evolution of such a system will be. And that's what we're planning to do for a lot of the galaxies and a lot of the galaxies in the groups that we've been studying. And here, for example, I'll point out 13% of the total group mass is in these tails. And we're still not 100% sure where these cells are coming from. Is it due to the interaction? It kind of looks like ramp pressure, but what's causing the ramp pressure, because this may not be a super dense environment as well. So this is some of the analysis that we're working on. And we then, in the end, want to put this in the context of other groups as well, because these are selected for particular properties. But as you saw, there's also the work going on with ACGs, and there are other kinds of groups out there. And we're also leading and involved in projects that try and address this by getting more H1 data to study these. And another key aspect of this I haven't mentioned, that's because we haven't done it really, is trying to really see if we can get simulations of the systems to understand them better, because we really need that in such complex cases where you have multiple bodies and this gas that's just flying around everywhere. And so I think that's sort of the future, a lot of this. And also see if there are trends with environment, because as I said, the groups can be very different. So do we see differing amounts of H1 in galaxies outside of galaxies, or just plain H1 we can't see, as a function of these differences in the different groups. And so that's some of the work that we'll be looking at. And also some of our groups have AGN, star formation in galaxies that have AGN. So then how does feedback on top of the interactions affect all of this? This sounds very complicated the more I say it, but these are some of the things we're trying to tease out and piece together to help us understand how group environments affect the evolution of galaxies. Thank you.
Thank you, Moses. That's a lot of work to do. Are there any questions? Yeah, there's just in the middle. If you can somehow get there.
Yeah, hi, Bruce Elmgreen, very nice. For these very extended peripheral H1, are there any examples of background quasars where you can get absorption and tell if there's cold neutral medium?
That is a great idea. I'm not sure that's something we can look at, because in some of the group environments, you do see sort of background continuum sources that are reasonably bright. So that's actually a great idea, and we can follow up on that. Thanks.
Yeah, Celine, go ahead.
Yeah, thank you very much. Lovely work. I wanted to ask about the last point you mentioned about AGN signature. So in some cosmological simulation, we find an indication of extra gas along the minor axis, especially when there's an AGN-driven wind. So I guess you have detailed kinematics of those objects and maybe some H1 maps. Have you looked in any trends of orientation?
So that's one of the next steps. So one of the groups that's in our sample is actually the Grass Quartet. And that's for a nice example of where we can look for that, but we haven't looked at systems that have a strong AGN. I think with OPT7, that's just CFIT. So in that, I don't think we see anything sort of along the minor axis, but in something like the Grass Quartet, we can look at that, for example.
Thank you.
Are there any further questions that I'm missing? Yeah, just right there, yeah.
And I'm Xichen Lin from Peking University, China. And I have two short questions. The first is on your kinematic decomposing the two galaxies and that you show. And last I saw a quite clear, actually, horizontal cut is there where you separate these two galaxies. And also you mentioned that the origin of the tail is very interesting. And what's your general direction to where to your general plan to find the origin of it?
Thanks for that. So yes, that cut, thanks for spotting that. That was just at some point we had to just make some cut to try and differentiate between them, because we looked at the galaxy in the velocity space, but at a certain point it's hard to really tell. So we had to make an informed decision on where to make that cut over there. So yeah, that is sort of a cut we made. And then regarding that, at this point, I think we really need some kind of more detailed simulations. There are previous simulations of the system that show that you could, or even similar systems, I think it's by Kurt Struck and other people, where maybe you can have such an interaction that leads to gas being pushed out of the galaxies that could form something that might look like some extended tails like that. But currently we think it's a combination of different things, such as possibly feedback and interaction. Whether there's any ramp pressure, that's a question mark at this point.
Thank you. We've run out of time for questions for Moses, so thanks very much again. And our last speaker of the session is Federico Lelli. He's talking about galaxy dynamics in a statistical H1 survey.
Good morning, everyone. I'm Federico Lelli from the Arcetri Astrophysical Observatory in Florence. I presume I don't have to convince this audience that H1 is one of the best possible kinematic tracers in galaxies. One of the main reasons is that H1 disks are much more extended than stellar disks, and so we can probe the gravitational potential all the way out to the outer region of galaxies. This is just one example of a nearby galaxy in which the inner parts of the rotation curve are traced using optical H-alpha spectroscopy, but at some point the H-alpha disk ends, and we can extend the rotation curve using H1 data. And in particular, this is the region where the discrepancy between the observed rotation velocities and the one that we expect from baryons, gas and stars, is very large. So where the dark matter effect really starts to kick in and where we can probe the dark matter halo with the highest possible accuracy. So over the past years, I've been working on the SPARC database, which is a compilation of 175 disk galaxies for which we have H1 rotation curves from the literature, more than 40 papers and PhD theses, mostly from the University of Groningen. We also have H-alpha rotation curves for about 30% of the sample that allow us to trace the inner parts at higher angular resolution. And then we have near-infrared photometry from Spitzer, which is very important because this is one of the best possible tracers for the stellar mass in galaxies, and therefore we can compute the red curve with high accuracy. So using the SPARC data, our team has been writing 26 papers, and many more papers were written by different teams. So I clearly don't have time to go through all this. I will just focus on a few highlights. An obvious thing that we can do is to test different dark matter halo models. These are two different galaxies, a high mass one and a low mass one, that are fitted with two different halos. In the middle panel is a Caspi Navarro-Franken-White halo, whereas on the right panel is the so-called Dicintio 14 halo, which is essentially baryon-modified dark matter halos coming from full hydrodynamical simulations. What you can see here is that for high-mass galaxies, there is not much of a difference, but when you go into the low-mass regime, the NFW halo is clearly not able to fit the rotation curve well, both in the inner parts and the outer parts. This is the so-called cusp core problem, where when you go through a dark matter halo that has been modified by stellar feedback, you can get a good fit. And this is not just an isolated case. Peng-Fei Li, in his PhD thesis, has been testing 7 different halo profiles for the entire SPARC database. Peng-Fei is now professor in Nanjing University. These kids grow up so fast. But what you can see here is essentially a plot that quantifies whether the fits are good or bad through the entire sample. You don't really need to understand what these axes mean. It's just that going up is good, going down is bad. Most of the halos fits in an almost identical way, so we cannot distinguish among them, but there is one that is clearly stand out to be the worst possible halo model that you can fit, and that is NFW. So I think we should, leave NFW to history books and move on. Another thing that we can study are empirical dynamical relations among baryonic quantities and dynamical quantities. A very well-known one is the baryonic-Tully-Fisher relation that relates the baryonic mass of the galaxy with the rotation velocity along the flat part of the rotation curve. So this is a relationship that formally applies for measurements for R that tends to infinity. Another very well-known, less well-known relation is the central density relation that now relates the central dynamical surface density that we can infer from rotation curves versus the baryonic central surface density. So this is a sort of inner galaxy counterpart of the Tully-Fisher relation that applies at small radii. And then we have the radial acceleration relation, which is a spatially resolved relationship that use each individual point in different parts of the rotation curve. And in particular here on the y-axis, we have the observed kinematic acceleration, v square over r, while on the x-axis is the baryonic gravitational field that we infer from the distribution of baryons. I don't have time to describe this in detail. I wrote a review for Nature Astronomy a couple of years ago that you may check. I will just give you 3 main concepts. The first one is that these relationships are telling us that there is a baryon dark matter coupling in galaxies that occurs at both global and local scales. And so it's important to ask what's driving this coupling between these two components. Secondly, these relations are extremely tight. Basically, the observed scatter that we measure is consistent with the observational uncertainties. And so a key question is whether there is an intrinsic scatter in this relation. Of course, we expect to be intrinsic scatter if those are relationships coming from the process of galaxy formation and evolution, which is entirely stochastic. But at the moment, we cannot really address this question. And the third important point is that these relationships were predicted a priori more than 40 years ago by Milgrom in 1983 using his Mond theory. And for me, this is a really important reason to take Mond seriously, because predictions are the essence of the scientific method. So if we don't take seriously a theory that made multiple predictions, I don't know what we should take seriously. And if you want to know more, I will give a review talk about this today at 3:30 in the focus meeting number 9 on dark matter that should happen in the meeting room 2.61. So if you like, you may come to my talk and then quickly move here for the other talks. Another important question regarding scaling relationships is whether there are any galaxies that deviate from them. If you go through the history of this subject, we can infer a sort of golden rule, which is that as the data quality increases, the scatter around these relationships decreases, and the outliers tend to disappear. But now and then there are claims in the literature about galaxies deviating from the Brioni-Talley-Fisher or other relationships. One of the most recent ones concerned ultra-diffuse galaxies. So I had a look about this, and today on the archive you can find a short paper by myself that has just been accepted for ANA letters. And in particular, I showed that UDGs do deviate from the Brioni-Talley-Fisher relation, but exactly in the same way as spark galaxies that have low inclination and low quality, low resolution data, which is actually the same situation that occurs in UDGs. So my interpretation is that there is nothing really special here. It's just that when you look at face-on galaxies with low quality data, they tend to deviate to the left for a number of known systematic effects. Now, Spark did very well, but of course it has severe limitations. One is that the sample remains relatively small, under 75 galaxies. So if we want to study things like possible dependencies on the large-scale environment or dependencies on secondary parameters that fix mass, like star formation rate or morphology or gas fraction or surface brightness and so on, we are limited. And so we need a bigger sample. And secondly, Spark was a compilation of rotation curves from the literature, so it's somewhat heterogeneous by nature. And if we really want to measure the intrinsic scatter of the dynamical laws, which we already know is below 25%, we really need to have a very good handle on the uncertainties. And this is not just a matter of using different telescopes, but also using the same strategy and the same techniques to derive the rotation curves and infer the observational errors. So these are both critical issues to test both MOND and Lambda CDM with galaxy dynamics. So we decided to build a new Spark database. This is our team. The hard work is done by 2 PhD students, Konstantin Haubner in Florence and Francis Dewey in the US. Basically, the European leg of the team is doing H1 analysis, deriving rotation curves and gas profiles in a homogeneous way using 3D Barolo, whereas the US part of the team is doing a surface photometry in the near infrared, in particular using WISE in combination with stellar population synthesis models in order to have the full stellar mass profile for these objects. And at the end, we can combine everything to have full mass models similar to the ones that we had for Spark. So we started this project by collecting H1 data cubes from various telescope archives like ATCA, GMRT, VLA, and Westerbork, and we ended up with about 1,000 galaxies. So we call it Spark 1K. These are basically the same galaxies from the targeted H1 surveys that Erwin has been describing in his review talk. Later on, we thought, well, maybe we could be a little bit more ambitious than this because there are the Wallaby DR1 pre-pilot survey data, which Tobias has been describing. And we also got in touch with Adam Leroy, which is leading a VLA reanalysis project called Everythings. And we ended up with about 2,000 galaxies. So we increased the sample quite a lot. But then we thought, oh, maybe we should also get in touch with the Aperitif team that was happy to collaborate with us. And so the project quickly went up to 4,000 galaxies, and we now call it Spark 4K. And we decided to stop here. Otherwise, these 2 PhD students will never graduate, and they will not look so happy at the end of their PhD. So this is the sky distribution of the current Spark 4K sample. We are mostly probing galaxies in the north from the historical Westerbork telescope in blue, the Aperitif data in red, and the VLA data in yellow. In the south, we have much less galaxies, mostly coming from ATCA, the Elvis compilation, as well as these dense regions, which are the Wallaby pre-pilot fields. But of course, in the near future, as described by Tobias, the southern sky will be much more better probe thanks to Wallaby. This is the distance distribution of the sample. just meant to show you that we're mostly probing galaxies at small distances within 50 megaparsec, but there is also a tail towards higher distances where we find the most massive H1b ring objects. And just for reference, this is the previous Spark database. So this is going to be really an order of magnitude increase in the number of galaxies. Just one example about a well-resolved galaxy in our database coming from things. I will not enter in detail, I don't have time. I will just say that for objects that are observed with such a high resolution, it becomes very important to model warps, so variation of inclination and position angle with radius, and 3D Barolo is quite good at doing that in an automated way. This is the opposite end of the spectrum, a poorly resolved galaxy from Atlas 3D. This is actually a dwarf around a massive elliptical, which is resolved only with 2 resolution elements, but we can still get some rough idea of the rotation velocity as well as the geometric parameters. And finally, let me say that Spark is an intermediate, yes, necessary step towards the future, because as we heard, Wallaby will provide many spatially resolved galaxies. Here I write 20,000. Maybe I'm too optimistic, but something of this order. And then Meerkat will transition into SCAMID and may provide many more objects spatially resolved depending on how our community decide to carry out the H1 surveys. So to conclude, Spark 4K is expected to provide mass model for 4,000 galaxies. It will enable lots of science such as dynamical scaling glows, dark matter halos, and so on. And this is a necessary step to get ready to the sky revolution. Thank you.
Thank you very much. I'm going to start with Betsy because she's chair. So.
Thank you, Natasha. Yes, so Betsy Adams. Very awesome. I'm very excited for this. But when you put up your distribution of velocities or distances, I did have a thought, which is, what are you going to be doing about distance uncertainty, and how is this going to become a limiting systematic that's going to limit, sort of a push to less scatter?
Yeah, in this plot, for simplicity, we're just applying the Hubble law, but actually we're using the extragalactic distance database from Tally to get proper distances. And we have 250 direct distances from tip of the red giant branch, Cepheids, and supernovae. For the rest of the sample, we are using the cosmic flow tree calculator that is essentially a fancy Hubble Hubble law that accounts for the peculiar motion. So I would say that we will be able to calibrate the dynamical laws with direct distances with 250 galaxies, which is already a lot. And then the rest will be using cosmic flows.
Hi, Federico. Thank you very much for your talk. So you showed us 4,000 galaxies, but what we learned also from your paper today, in order to be able to measure rotation curves and put your galaxies on Tally-Fisher relation, galaxies should be perfect. They should be resolved. They should have high signal to noise ratio. They should not have disturbances and all the other things, and they need to be resolved with 5 beams across the minor axis and with inclinations more than 45 degrees. So when you do all those cuts, what would be the real number of the sample galaxies? Because Christine showed us Wallaby galaxies and they did a fantastic job to get the rotation curves, but the signal to noise ratio is still pretty low, plus the inclinations cut and everything.
Yeah, no, I agree. In fact, the idea here was to first collect everything that we could collect and then later on do quality cuts when we study specific relationships. I think that these 1,000 galaxies are very solid because they come from the targeted surveys at high angular resolution and sensitivity. When we add also the Upper Teeth and Wallaby data, of course, many of these galaxies will have low signal to noise and low angular resolution. I would say roughly that maybe half of the Spark 4K will be usable in terms of really nailing down the observation, so maybe 2,000.
So in the interest of time, we've just run over a little bit and we all want to go to lunch. So I thought all of the talks were beautiful and everyone stuck to time. So thank you very much again to all of our speakers in the session, and have a good lunch, and we'll see you in the next session.
would recommend that you stay inside. Some volunteers had come and
points, I think. Oh, that's a good question. Is it better? It's there. Hello, everybody. My name is Barbara Catinella, and I will be chairing this session. I look forward to the fantastic talks. And so, yeah, we are on a time, a tight schedule, so we'll proceed. So our first speaker is Mpati Ramatsoku, talking about environmental processes traced by H1. For all speakers, I will give you 2 minutes warning before your talk time is over. Thank you.
Cool. Okay, this is on. Hi, everybody. Good afternoon and good morning and evening to those of you online. My name is Mpati Ramatsoku, and I was told to highlight some of the recent advances that we know of regarding environmental effects as traced by H1. And so like the speakers who spoke this morning, this will highlight most of the work that I am aware of. I'll be focusing on resolved studies in between redshift of 0 and 0. So very, very, very local. So to start with, I wasn't even quite sure whether to include this. How do I? Is it transitioning? Okay, cool. This is a slide that I always like to start with. This is a beautiful simulations from the Illustrious TNG project by Dylan Nelson. It's on YouTube. It's beautiful. It has Bach as a theme of this simulation. And what it's essentially showing are all the different processes that could occur in galaxies within their environments. And what we know about these environments is that these effects, external effects to be specific, is that they can basically be categorized into 2 categories. You have your hydrodynamical processes, which affect only the gas component of galaxies as they interact with the ICM or IGM. These include processes like ram pressure stripping. You might get things like thermal evaporation when galaxies are interacting with this hot medium. Things like viscous stripping could take place. And you could even get enhanced turbulence, which causes accretion. But you also get gravitational interactions, and these ones affect both the stars and the gas phases of the galaxies. And this includes things that we've heard about this morning, like tidal interactions and tidal truncations. You might have galaxy mergers if galaxies are moving at relatively low speeds, or even flybys if these galaxies happen to be flying through the orbits of each other. And the picture that is starting to form is that these tend to act together. So you don't have one single process particularly dominating in one environment or the other. And I will talk a little bit more about that in the coming slides. So the way I like to think about environmental processes is I always like to start from what do we know from unresolved studies, and then I move down to what we know from resolved studies. This is a nice plot that I like very much from Antonino Marasco's paper. And here they're showing H1 deficiency as a function of the projected distance from the cluster centers to the outskirts. And what you're seeing is that the deficiency tends to increase as you get closer to the galaxy clusters. But this is for really, really massive clusters. We are talking the coma clusters and the norma clusters of the universe. So masses of around 10 to the 15. So anything greater than 10 to the 14, with a lot of hot gas. And in the center of these galaxies, you have very dense dense ICM, and you have galaxies moving at very, very, very high speeds. We have seen these images over here. I'm surprised I haven't seen them today, actually. It is from the beautiful work, the Viva survey by Ri Chang, where they were showing a number of galaxies. These are just the two that I chose at random because I see them at every conference, showing you the effect of RAM pressure stripping. And you can see that in these two images, for the most part, the stellar disks remain undisturbed. But you see that these truncated disks and these one-sided H1 tails that don't have any old stars within the tails. And I emphasize the old stars bit because we had a look at some of the extreme cases of RAM pressure stripping, and these are in the so-called jellyfish galaxies. These are the two galaxies from the GASP survey, which are selected to really just find these galaxies that are experiencing this RAM pressure stripping. And in these specific galaxies, and this is ISO 137001 that most of you know. And in these types of galaxies, we see this extreme form of RAM pressure stripping. These galaxies are moving at very, very, very high speeds. I implore you to go look at the papers if you'd like to know more. And in these specific galaxies, you do actually see some stars in the tails, but these are not all stars. These are stars that are forming in those tails from the stripped gas. But I will not go into any more details about those, and move on. And in galaxy clusters, I think we kind of know a little bit how to infer the info time scales of galaxies in these environments. So I like this paper. This is by Ri, 2017, which is sort of showing you the timescales of galaxies falling into galaxy clusters. You see here, this is the infall time and the mass loss fraction. And you could look at the different parts of this phase space diagram, which is the velocity of the galaxies relative to the cluster as a function of the projected distance. And you can sort of look at where the galaxies tend to be in this phase space diagram. And you can kind of infer from this where or how long the galaxies have been experiencing specific external process. Like in the center, where RAM pressure would be most well, I don't know, dominant, if you will. So I think in galaxy clusters, we kind of have an idea of what is going on, especially if you're talking about large clusters, because these have been studied so much in the past. But what do we know about the groups? We have already seen this plot over here from the compact groups of loaders compared to groups from choirs that Moses Mokhotsi spoke about this morning. And what I interpreted from this plot is that, yes, there is H1 deficiency. It's not as strong as what you're seeing in the galaxy clusters, but there isn't any strong correlation with the distance from the centers of the groups. This is H1 deficiency as a function of the projected distance from the group centers from a paper a while ago. So we're not seeing this sort of increase as you go to the cluster centers. This is a completely different environment. So galaxies in galaxy groups move at relatively low speeds. So we expect to see frequent mergers and tidal interaction. And this has already been shown. Beautiful M81 group. We've seen this in the Leo ring, which is showing these nice streams of gas that's been removed from the disks of galaxies by tidal interactions. So, and in groups, typically you don't expect to find X-ray emitting IgM or intergroup medium or intergalactic galactic medium. And so yes, we have always believed that the gas is removed through these gravitational interactions. But I think that picture is changing a little bit. Because, and this is just a nice gallery of what we know, or the different processes that we've seen in action from the Higgs compact groups, from the Jones paper that they released last year, showing all the HCG groups that they have studied so far. So I really like this if you want to look at pretty H1 images. But Moses Mokhotsi this morning has already shown this picture over here, which shows this nice interacting pair of galaxies. There's another galaxy over here and another one over here. So we do see that tidal interaction is happening in this galaxy for sure. But we're also seeing these one-sided tails that could be due to REM pressure stripping. The morphology seems to be that of a galaxy undergoing REM pressure stripping. Or it could just be an interaction between these two very, very huge galaxies and this one tiny galaxy over here. I spoke to Mo actually before giving this talk, and I asked, "Do you have any X-ray in this region over here?" And it isn't clear because there isn't a huge X-ray emission in this group, so it is not certain how this tail has formed. So it could be REM pressure stripping, maybe. And I say maybe because we have seen similar cases in the Phonex cluster that Filippo will talk about later on. This is the work by Paulo Serra, which was published recently, last month. Although the Phonex cluster is not a group, it's a Phonex cluster. It's a very tiny cluster. It has a mass of around 10 to the 13. So think of it as a large group. It has an electron measurement of around 1.3% that of the COMA cluster. And this is from XMM. So it's not a huge cluster. And from these studies, Paulo and the team found an inversion, which you see over here, close to the galaxy disk, at an inversion of the velocity gradient close to the galaxy disk, which you see over here. But then you also see a velocity gradient, which is due to REM pressure stripping. And this is one of the few cases where you could actually see tidal interaction and REM pressure stripping occurring in one galaxy at the same time-ish. They didn't only find this in this galaxy, they found it in many other galaxies within the Phonex cluster. This is just a subsample of those galaxies showing these nice long tails, which could be due to REM pressure stripping. They have velocity gradients consistent with REM pressure stripping, but all of them, in fact, all of them show these disturbed optical morphologies, which indicate that at some point they might have gone some tidal interaction or tidal perturbation. And what the authors of that paper say is that it appears that the tidal interaction could have disturbed the H1 such that you don't really need a lot of X-ray or a lot of ICM pressure to actually remove the H1 from the stellar disk because it's already puffed out of the disks. And so REM pressure kind of just shades these long radially oriented tails. So this is quite exciting to actually see because then it might explain what we're already seeing in galaxy groups such as those shown earlier by Mokhotsi. But then what do we know? But then what do we know in filaments? So we're getting an idea of what's happening in galaxy clusters. The more sensitive observations get, the more interesting things appear to be. What we've seen in galaxy clusters in galaxy filaments in recent studies is that it appears that the number of H1 poor galaxies seems to increase as you move closer to the filament spines. This is the work that was recently published by Munira Hussain. But there's, and this was already kind of known from earlier studies, like this one that I'm showing over here, but there's a little bit of a disagreement about the mass stellar range where these results hold. In fact, in a work by Kleiner et al., they found that actually in the high mass range, what they're finding is an excess of H1, which could indicate some kind of accretion, when you get closer to the filament spine. So we still aren't quite sure what is happening in galaxy filaments. In fact, what Munira or what Hussein and the team did was they separated the galaxies that are within the groups, within those filaments. And what they're finding is that the fraction of H1 poor galaxies actually kind of flattens out. And so what seems to be happening in this filament is that this deficiency or this H1 deficiency is actually driven by the local group environment as opposed to the larger, as opposed to the larger large-scale structures. So just really quickly, we have started looking at filaments that are close by. We're looking at filaments that are feeding the Virgo cluster. And what we've found is the same thing that has been found by a number of authors, is that you have H1 deficiency sort of increasing as you get close to the filament. So there's a little of a picture forming there, but it's still not quite clear. This is the work by Gianluca Castagnani. And so what we did was we observed the Virgo filament, the one that we could access with Meerkat. This is Virgo 3. We pointed at it using about 15 pointings, looking at regions where we had lots of galaxies to maximize our output. We get down to column density sensitivities of around 10 to the 19 at 30 arcseconds, but we also are able to study the disks of these galaxies at quite high resolutions. This is the work that I'm doing with a postdoc at EPFL, Gautam Nagaraj. He told me to show this picture. This is a moment zero map overlaid over the legacy image. This is a Meerkat field of view of 1 degree. And we are starting to see some interesting things within this Virgo 3 filaments. For example, in this region over here, we see these two galaxies that seem to be interacting. They're showing one-sided tails towards each other. But what you're also seeing is this compression on one side, which would be more consistent with a REM pressure stripping happening in this filament. This is the filament spine as it's moving through the group. And so we're seeing a number of things happening in this environment, which seem to be mainly driven by the actual group environment as opposed to the large scale structures. So we don't actually know what is happening here yet. And what we did was we looked at the galaxies that are closer to the filament spine to see if there's some trends with the H1 asymmetry. And at first glance, you might say, wow, okay, it looks like galaxies that are closer to filament spines tend to have more disturbed H1 morphologies than those that are further from the filament spine. But that is not actually the case because there's a lot of variation when you look at the group environment. So it seems that all of those variations are caused by the local group environments or association. So just to sum up, I will leave this here. I think we kind of have an idea of what is happening in galaxy groups because we studied them for such a long time, and we sort of have a handle on how to infer the time scales of these processes. But the picture is not as clear in galaxy groups and in filaments. And as the instrument gets very sensitive, the picture becomes even less clear. So I will leave you here with these questions over here that we're still yet to address. And if we get more resolved observations of these kinds of environment, maybe we could start addressing them. Thank you.
Thank you very much.
Sorry.
Time flies, I know. Questions for Mpati? Maybe let's start with the early careers, if we can. From anybody? Look.
I'm Patti, Luca Cortese from ICRA UWA in Perth. Thanks for the nice review. I'm very intrigued by the last part about filaments. So most of the work in the past have kind of ignored about groups and just look distance from the spine. But you made the case that what you are seeing at the moment is probably just because the groups are actually close to the spine and the filaments, and what we are seeing is more a group environment and not a filament environment.
Yeah.
So what's your take on that?
No, but I think that is an important point. So we have tried to separate the galaxies that happen to be close to the environment. And as I mentioned, you find that there's this rise in H1 deficiency or in the symmetries. But if you were to look at the entire environment as a whole and look at the local associations of these galaxies, they're actually in the group. So what is doing the heavy lifting are the processes that are occurring in the groups. We have no idea what the filaments spines are doing at the moment. It's still very unclear.
Thank you. Unfortunately, we need to move on. Thanks, Patty, again. And our next speaker, another invited talk by Jin Wang, talking about the new lessons from wide field H1 surveys.
Thank you. Thank you. I'm very happy to share my perspective of what we have learned with this new wide field H1 surveys. There are many benefits, many advantages with wide field H1 surveys. In this talk, I can only focus on two of them. The first aspect is that it is wide, allow us to see the link of galaxies to the surroundings, both the group environment and the CGM around galaxies. The second aspect is that it's bland. It has no selection other than H1, so allowing us to explore in H1 and discover in H1. It has some advantages compared to an optical bias survey, for example. And because of these two aspects, in my talk, I will mostly focus on how galaxies obtain and lose their H1 through interacting with the surrounding environment, and how those H1 is used to replenish the star formation or the galaxy if not has enough H1, resulting in quenching of that star formation. And in this talk, I will be biased toward the two surveys. One is ASCAP. Each pointing has a field of view of roughly 30 square degree. It allows us to map a lot of groups and clusters out to several times the visual radius. The second survey, arguably, is FIST. I conducted with FAST. Each field of view is at least 1 square degree, but to be fair, the width on each side is 20 times the primary beam of FAST, much higher than that of ASCAP. Firstly, we'll focus on the group environmental effects studied with Wallaby with ASCAP. As I said, it will cover a lot of groups clusters out to several times the visual radius, giving us the opportunity to coherently study the gas-rich galaxies all the way from the info region to the visualized region. Typically, these type of H1 bland surveys are blamed for their being biased toward gas-rich galaxies in study of general galaxy evolution. But in this topic, this become actually an advantage because it helps us escape from the nature or nurture problem. The H1 selected sample almost certainly first time enfolders. We need not worry about the population that probably assembled into the system at a redshift of 2 or earlier. And the ASCAP also have other advantages. The resolution is moderate, 30 arcsecond. It avoids a lot of confusion we previously would have with single dish observations. And furthermore, the resolution allows us to study the ongoing environmental process. And in my talk, mostly the run pressure stripping and the tidal stripping. These are some very traditional models about these two processes. We just converted the model a bit so that they can easily be applied to observables that can be obtained with these H1 surveys. You can see the H1 surface density in both
semi-analytical models. So we really need to resolve the gas in order to apply them to understand how H1 is processed, stripped by these two physical processes. Normally, when we study environmental effects, how galaxies evolve under them, we would quantify the environments with the local densities, the distance to BCGs, the halo mass, and then try to relate them to the consequent H1 richness or deficiency. By the way, lost what's happening in the middle. Now we can fill in the gap. We approach it from a statistical point of view. We target the coherently all the H1 rich systems in a group or cluster. By the way, can study the ongoing processes, these two physical processes. We selected three representative systems. Each of them have some signature environmental processes. One Hydra, we expect their own pressure stripping to be more significant in it. And then Aridona's supergroup is three groups that have almost equal masses merging together. So tidal effects should be very strong. And finally, a very normal looking boring group. We expect the both effects to coexist, and we will try to disentangle them. We start with the Hydra. I need to mention that, to be fair, the 30 second resolution resolved the H1 in many of the systems, but not all of them. But luckily, there's a very tight size-mass relation for the H1 disk, and there's a similar outer radial profile for the H1 subdensities. So we can do the quantification of stripping. We can quantify subdensity in a hybrid way, the real detection, and to predict it from those scaling relations or self-similar radial profiles. We can use two measurements to cross-check each other, use the real observation to test, to validate the predicted subdensity profile method. And it turns out that they really work well consistently. So we were able to quantify that in this Hydra cluster, the run pressure stripping for this first time in fuller H1-rich systems, they are quite prevalent. Within 2 times the virial radius, 1/3 of them are under some level of run pressure stripping. If we count within the virial radius, 2/3 of them are under the stripping. So it really starts early. But the run pressure stripping for most of the systems, they tend to be mild. If we're subtracting the currently strippable gas from the total H1 mass, many of them only move slightly on the relation of H1 mass as function of stellar mass. So they are mild effects, but they accumulate for a long time. If we pretend to put the galaxy at different distances so that we can quantify when the stripping starts, and we also can quantify how far the galaxy can inflow into the group or cluster before most of the gas is stripped. We can quantify these 2 timescales, the stripping time for the strippable gas and the depletion time of the gas. Then we can find that the stripping time for the strippable gas is quite fast, within roughly 100 million years, but the depletion time can be quite long, like several hundred to 1 giga-year, several hundred million years to 1 giga-year. It's mild but a lasting long process. Then we look into the tidal effects with the Arizona supergroup. If we focus on the low mass systems, we check how the H1 diameter over optical diameter change as the tidal strength parameter. The size ratio indicated the shrinking of H1 disk because of the stripping process. We can see an anti-correlation there. It is worth mentioning such an anti-correlation is not seen for more massive galaxies. So under stripping, the H1 disk shrinks outside in. This is very consistent to our expectation, very good. But unexpectedly, if we look into the color gradients, which means well, the color gradients shows that the galaxies, because of the stronger stripping, the redden inside out. The gas is stripped outside in, but the filling for the star formation seem to first loss from the inner disk instead of the outer parts. Finally, we are looking into a more common group where both effects should coexist. And we put a lot of observational effort onto it. We obtained it's a first fast S-cap synergetic observation field. And we also obtained the cell images with ARMA for 20 galaxies. We also obtained the H-alpha narrowband imaging. After quantifying both effects with the models we just showed, indeed, the two effects coexist it affect around 80% of all galaxies, but for each effect, they can affect a different group of galaxies. How we disentangle these two effects, how we are sure we successfully disentangle them, how they could have separate or co-working effect on gas stripping and star formation, please attend Lin Xuchen's talk tomorrow. He will give more details on that. Finally, this S-cap wide field view allows us to select a lot of gas-rich pairs. Previously, if we start from an interferometry point of view, we cannot have so good statistics. If we're from the single dish, we usually have to blend the H1 from the two galaxies of the interacting pair. But now with S-cap, we can have a statistic sample, and we are allowed to deblend them simultaneously. And with this new sample, we were able to find that the low mass and high mass galaxies in interacting pairs, they behave differently. It is commonly known that star formation rate is enhanced in gas-rich interacting pairs. But for low mass galaxies, we found that the star formation rate enhancement is more tidally driven. It correlates with the tidal for high mass galaxies, sorry. And for low mass galaxies, instead, it is not tidally driven. It's flattened here. Instead, it is enhanced when the gas disk with the neighboring source encounter each other. This is where the H1 disk of the two start to collide into each other. It's more hydrodynamic effects driven process, likely the shocks caused by the collision. Now I'm to turn to the interaction with the CGM with the phase survey. It is conducted as fast. We map the H1 out to at times the lower between 1 degree and 8 times the characteristic radius quantified as 1 solar mass per pc square asymptote radius. So it's quite a wide field view for each galaxy. Currently, we have 55 galaxies observed. They are quite gas-rich and star-forming. It's not a complete sample, but it allows us to see for the first time how the H1 interact with CGM for so large a sample down to a column density level 5 times 10 to the 17. And in this talk, I will focus on one aspect about the diffuse H1 that interferometry does not see, but the fast single-dish telescope can see with this total power imaging capability. Previously, we know interferometers in principle must miss large-scale gas. The question just was, how much is that? Where is it distributed? And what's the kinematics like for a large sample? The diffuse H1, as I illustrated here, is the difference between the total H1 and dense H1 previously detected by interferometry. We take the thin sample, a subset of the thin sample as a reference sample here. We found quite a diversity, but on average, the thin galaxies, they miss 10% to 50% of their total H1. If we quantify this as a functional column density for the overlapping regions of the dense H1, diffuse H1, then down to a column density of down to a subdensity of 0.5 solar mass per pc squared. The missed offset, the offset is roughly 0.5 dex. And in other column densities, it's a constantly 0.25 dex difference. So this indicates that the missed H1 is not only important in the outer part, the low column density region, but also in the high column density region where the dense H1 interferometry can safely, I believe, safely detect many of the H1 there. Because of this change in column density level, so it is expected that many known scaling relations change. The size mass relation, first of all, changed, although I did not show the figure here. The scatter is larger. Thank you. And the star formation law change because H1 subdensity shifting rightward, the star formation in outer disks beyond the R25 become more inefficient than before, and the scatter is larger. And interestingly, the scatter revealed to have better dependence on stellar mass than before. If we come back to the question of interacting with the CGM, the diffuse H1, if we quantify its kinematics, it is rotating in the same direction as the dense H1, but in a relatively lagged way. The lagged level is like 50% to 25% within the co-spatial region. And the velocity dispersion of diffuse H1 is twice larger. So it looks very much like the thick disk detected very well with the halo gas survey and now with the Mongoose survey. If we look at the outlying diffuse H1 in general, both within and beyond the dense detected regions, we assume it to be in pressure equilibrium with the surrounding CGM. And then we found its scale height and column density correlate very well. It indicates almost a constant volume density, which means almost a constant cooling rate, indicate its nature as a cooling interface of the CGM going through into the ISM. And if you look at the scale height as a functional radius toward a large radius, interestingly, it does not flare up. It goes down because of the pressure exerted by the CGM. Another way of looking into it, you look at the scale height by selecting adjoint sample with the kinematic inclination above 85 degrees. We quantify the height where the column density reaches 10 to the 18, sorry. It has a range between like 15 kiloparsec to 50 kiloparsec, and there's a correlation with the total H1 mass. Interestingly, this trend and this typical value are not well reproduced by the TNG or illustrated simulations. I skip that. I want to say that it gives very good idea. Can let us cross-check when we combine the direct mapping of H1 and the absorption line studies. Basically, at a given radius, as a diversity of absorption line study suggested column density, and our lesson is that they possibly reflect the inclination of the galaxies. Finally, I want to show the diffuse H1 fraction seem to be correlated with the level of tidal interaction. This makes us to ask whether tidal interaction is causing the loss of H1 or the accretion of H1 through production of this diffuse H1. We have several evidence for the accretion side, for the replenished part. To see more details, please attend Ning Xuchen's talk again tomorrow morning. And I will skip the alpha side and deal with my summaries. Sorry.
Thanks, Jing. Question for Jing.
Hi, Jane. Thanks for a great talk. I'm Patti Ramatsoku from Rose University in South Africa. I was quite interested in your quantifying RAM pressure and tidal interactions, but I didn't quite understand how you define your strippable guess and how you define that could be tidally removed. Could you please?
In both cases, it's more or less like comparing the restoring force of the galaxy because of its gravity and the stripping force. And then when the stripping force is higher than the restoring force, then it is defined as the strippable.
First of all, it's nice to see the environmental dependence of the low column density distribution. I think that agrees with what we're finding in Mongoose as well. I had a question about the feasts. I mean, we talked about this a few times already. Of course, you're comparing it to Philae data or Westerbork data, which we know doesn't have that many short baselines. Meerkat does have a lot of short baselines. So do you have a feeling for how much of a correction Meerkat would need if we were to observe our galaxies a bit fast, for example?
Thank you for asking this. I also have the same question, and my 2 cents is that I think for the systems that have their H1 extension all the way reaching the primary beam or Meerkat, we should have similar values because that's also the limit of the short spacing.
Okay, let's thank Wang again, Jingwan again, sorry.
Thank you.
And our next speaker is Graham Laurie, talking about the serendipitous Meerkat discovery of an H1H galaxy group with megaparsec scale filament structure.
Is it on here? Sorry. Oh, okay. Okay, cool. Cool. Hi everyone. Yeah, I'm Graham Laurie. Thanks for the introduction. I'm a PhD student at WITS, working with Prof. Roger Dean, and yeah, just like to thank the organizers for giving me the opportunity to present this, which I think is it's a pretty cool serendipitous H1 discovery. Okay, so just diving into the data, we actually used MGCLS data. That's the Meerkat Galaxy Cluster Legacy Survey. And more specifically, we used 2 L-band observations of the galaxy cluster Abell 3365. So it's observed for about 10 hours each. So we've got a total of 20 hours, making it relatively deep, which is quite nice. We just follow a standard protocol in the calibration. So we use OxCat and 1GC and 2GC. And then we do continuum subtraction in 3 steps, 2 in the UV plane, and then ImConsub after we make our cube. So the cube properties, it's got 30 by 30 arcsecond restoring beam. We get an RMS of about 52 microjansky. And then our spectral resolution is fairly coarse. It's 209 kilohertz. So at the discovery redshift of 0.04, that's about 50 or 46 kilometers a second. Yeah, pretty coarse, but still pretty good. Okay, so what did we find? Well, the first thing I'd like to mention is it's really important to image your entire data set, because if we didn't, we never would have found this. But this is in the foreground of the cluster. So it's completely unrelated cosmologically to the cluster. Here I've just got an image of the group, but it's essentially, this is a DES image, dark energy survey, and then I've overlaid the contours, the H1 contours at 1 × 10⁻⁹. So yeah, we find this group, and it's got is there a pointer on here? Okay, it sort of runs like from north to south. I'll show you a better picture of it just now. Okay, but naturally we want to run source finding once we find this to make sure we don't miss out on any galaxies. So we use SOFIA 2. We use the standard smooth and clip algorithm, and then we run it at a fairly low threshold of 3.4 sigma and 0.7 with a reliability kernel that we sort of fine tune through the Skellum plots. But the reason it's quite low is because we've got DES imaging, and it's not exactly a massive sample, so we just manually cross-check that. And we end up with 35 H1 sources. But not all these sources are part of the structure, right? So this is sort of a challenging thing, but which of these sources are associated to one another? Well, there's generally 2 ways you can do it. One is with dark matter halo finders, and then the other is just friends of friends. So we take the more naive approach and we just try friends of friends. These linking parameters that I've listed up here are sort of inspired by other friends of friends algorithms that have been run on like SDSS and 2MAS. So yeah, we run these, and we find that the orange galaxies over here are linked by this friends of friends algorithm. So in this plot, the orange galaxies are linked. The gray galaxies don't get linked at all. There is actually one over here that like these two are associated, but I didn't link them into a separate thing. So for the most part, the gray galaxies are isolated. And then the H1 mass scales, or the markers scale with H1 mass. And then the red cross is our geometric mean. Okay, so I guess I lost my confidence intervals, but yeah, so we compare it to some scaling relations. So we calculate the star formation rate and the stellar mass using the Kluver relations, and then we find that, again, I don't know, I lost my confidence intervals, but they all fall within 3 sigma. There are some outliers, like this guy over there, but the outliers are almost always explained by either interactions or just Y's cross-matching gone a little bit wrong, because you can see in the DES imaging that there'll be 2 galaxies and then Y's just picks one up in the catalog. So yeah. Okay, so within this group, we find a more compact group of these 4 galaxies over here, and there's lots of pretty cool stuff going on here. So you've got like tidal interactions between these 2 galaxies with this extended H1 emission. And then over here, there's reasonable evidence for ram pressure stripping. So we've got compression of the contours on the northern side, and then this tail that extends. But yeah, it potentially due to tidal interactions first with these 2 galaxies, and then ram pressure stripping. We haven't really looked into it too much, but yeah, so all these galaxies fall within 220 kilometers per second, which is pretty close in spectral space. And then this bounding box is like 300 by 500 kiloparsec. Okay, so this is just a bit more information about those 4 galaxies in particular, but we also have other cool interacting systems in the group. So just something to note here is like this potential merging system where we've got 2 galaxies in the DES, this little H1 cloud extending out there. And then there's also radio continuum over here, so potential star formation rate or AGN activity. And then this is just your Wise band. Okay, so I've just listed some of the structure properties here. This thing is really extended from the northernmost to the southernmost. It's 4.15 megaparsec. This is its redshift. But what makes this really interesting is we've seen this all before, right? With Shilpa Ranchit had this discovery a while ago, and it's very similar amount of galaxies at a very similar redshift. And then just a couple of months ago, Marchin has this discovery of all these cool groups, and one of them is almost exactly the same, right? 26 galaxies at a very similar redshift. So we asked ourselves, like, how good is Meerkat at discovering these things, because it seems to be happening all the time. So in order to probe that, we got together with Ramil and we looked at SIMBA. So essentially, we make a bunch of light cones in SIMBA, and then when galaxies meet a minimum detection threshold, we try and group those galaxies together. And then when we find those galaxies group into structures that meet these criteria, then we define them as analogs. This is sort of arbitrarily chosen, but it's just to exclude the really small compact groups, as well as the massive filamentary structures. So yeah, just plus minus 10 galaxies from what we found, and then 1 to 8 megaparsec. And yeah, the H1 mass is listed there. Okay, so I've just picked 4 scenarios of what we see in these light cones, but we do many realizations to get our results. So what's happening here is the gray dots are all SIMBA galaxies above a certain H1 mass cutoff. The blue dots are structures or galaxies that are detectable by Meerkat and then also grouped into analogous structures. And then the red is for a comparison to a very similar observation with SKA. So that's essentially taking an analog observation of also about 20 hours, but you account for the increase in the collection area of adding about 80 SKA dishes. So in the first situation, we see that both Meerkat and SKA will detect a group, and this is sort of exactly what we're seeing at the same redshifts. And we're finding a bunch of these serendipitously, so makes sense. In the second situation, SKA really shows its power. Meerkat wouldn't be able to associate any of those analogs. I mean, it'll be able to detect individual galaxies within them, but not group them together. So it's like the individual galaxies that SKA would detect would glue these structures together. And you also see the filamentary nature in things like this, at least from the redshift slice. They do also appear like this if you look at the front of it, though. Then you've got situations like here where there's clearly a filamentary structure, but it's all below a detection threshold, so we don't find anything. And then there's a final situation where SKA detects a whole other filamentary structure that Meerkat would miss, but not only that, it also enhances the Meerkat detection. The galaxies that Meerkat do detect by adding individual galaxies to the structure. So over here, I've just explored some parameter space just to see how extreme this detection is, and turns out it's actually not all that extreme. Perfect, thanks. Turns out it's not that extreme. So this is our detection here. This is the cross. This is the maximum distance between any two galaxies within the analog. And then it's just H1 mass on the x-axis, and it's colorized by redshift. So the open circles are SKA analog detections, and then the closed circles are Meerkat, or the solid circles are Meerkat detections. So we fall well within the scatter, and yep, I mean, we can expect to see many more serendipitous discoveries like this. And basically, if you point Meerkat in any direction, it's likely, I mean, 0.13 groups found per pointing in any random direction without selecting where to look. And then SKA also would enhance these detections. So in summary, really look through your data and image it all. Don't just select a frequency range, because you can come across really cool stuff. And then this provides us with an awesome environment where we've got lots of interactions. I didn't show everything, but we've got H1 bridges and some compression and the RAM pressure stripping, which I did show. So it's a really cool environment, especially in this like early formation group stage, to probe interactions and environmental effects like Pati was talking about. Yeah, and then just this isn't that rare, at least if we take it into context of the Simba simulations. We can expect to see many more discoveries like this. Thanks.
Thank you, Graham. Perfect timing. We have a couple of minutes for questions.
Hi, Graham. Thanks again for the great talk. So when I was looking at the spatial distribution of your group, it seemed to be elongated north to south. Do you know if it's associated with any large-scale structure nearby at 0.04?
So we haven't used like disperse or any sort of filament finder. So we don't know if it's necessarily that large-scale structure. But yeah, we haven't really looked into that.
Hi, Graham. This is really cool stuff. I'm Natasha Maddox from Bristol. Either in your data or in the simulations, how many galaxies are in the structure, so within the group volume, that are not detected in H1, or are they all detected in H1?
Okay,
so these are H1 poor galaxies within the group.
Haven't really explored that in the simulations. And then we grouped the galaxies that were all detected in H1. So I mean, we would have missed in the empirical the data. We wouldn't have any. I suppose I can look for the redshifts of optical galaxies that are there and see if they're not appearing in H1. But yeah, haven't really looked that up. Thanks.
A very quick question. No, if not, let's thank Graham again. And our last speaker before the poster sparklers is Filippo Maccagni talking about the Meerkat-Fornax survey.
Good afternoon, everybody. And I'm Filippo Maccagni, working at the Observatory of Cagliari in Sardinia. And today I'm going to talk about the Meerkat-Fornax survey, which is a large project of Meerkat led by Paolo Serra, who is enjoying an adventurous holiday at the moment, so he could not be here. But of course, it's the work of many other people. Many of you are in the room. I didn't highlight them not to encounter the risk to forget someone. Now, why do we want to study Fornax, as also Patty introduced? Because we want to study the environmental processes that we always known that they shape galaxies. And as you can see from this very famous simulation, the evolution of galaxies happens in filaments and in small clusters, just like in our brain. This is a summary, very nice cartoon of all the environmental processes that can occur in with galaxies. And we are going to focus mostly on ramp pressure stripping and tidal interactions. And what we can do with Fornax and with H1 studies is that now we can go to study these effects to very, very low masses in H1 of a few 10 times 10 to the 6 solar masses. Now, this is the Fornax cluster seen in the optical with the VST. This is the center, and as it was already introduced, this is a small cluster. This is the X-ray emission onto scale, so you see that it doesn't really feel, not even the in center region of the cluster. And of course, here you see some statistical, the distance is at 20 megaparsecs, and of course it has been studied already, many other wavelengths. So we are going to focus on the neutral hydrogen. And we want to answer these fundamental questions. So can we find direct evidence of ongoing galaxy quenching in such a small cluster? What physical processes are driving it and on what time scale? Now, this is the footprint of the survey, which already has observed the cluster, and now we are going to visit this region. You may wonder why. If we're interested in the cluster, because in this region there is the group of Fornax A, which is has this large flickering radio AGN, which is likely falling onto the cluster. So even more processes of galaxy assembly. And this is not only scientifically interesting, it's very bright in the radio, so it gave us the opportunity to do Meerkat science verification on it. And I'm very proud because with one observation, we got 5 papers out. So 90 observations of Fornax in total. If it's a linear relation, it's going to be lots of papers. Now, I'm not going to talk about Fornax, but these are the references. I would like also to highlight, since it's an H1 crowd, you probably may not be interested in magnetic fields. You should. And this is also a paper that combined Meerkat and ASCAP observations. So that's why it's interesting. I will let you 1 second to take some pictures of this amazing slide. Now, you want to know more about Fornax A. So there is a poster tomorrow morning in the AGN symposium. And if you want, you can come to talk to me about it. Now, let's focus on the cluster. Of course, we looked at it even before Meerkat with the compact array. And here in green, you see the detections. And there is also a paper about the ATCA Fornax survey. And the sensitivity was about 2 times 10 to the 19, which, as we heard today, was quite already low in the log S regime. But now we will go to these mass limits with the Fornax survey, and this is the game changer. Here in green, you see again all the detections, and you see that even where we detected H1, we see much more. Now let's focus on this galaxy, NGC 1427A, and this very elongated tail. Here you see the complex of array observation, and here you see Meerkat, and you see that we go in with the gray contour in Meerkat is the same resolution, but we go 1 order of magnitude deeper. At the same but at the same sensitivity, we can go 3 times and we can resolve this tail in very high detail. Now, of course, it's not the only tail that we see. We see all these other tails, as also Patty mentioned, that they're all oriented towards the Fornax center. And their kinematical velocities is consistent with ramp pressure stripping. So we think that as entering into the cluster, these galaxies have been stripped. But if we look at the optical, we see also clear signatures of tidal interactions. So these two environmental effects must coexist even in such a small cluster to shape our galaxies. Now, we can do, because of the detailed observations and the high resolution, we can do very detailed studies. So again, we see NGC 1427A, the optical body, the elongated tail, but we also see very many clouds associated to it. So this is evidence of RAM pressure that we can investigate, but the RAM pressure is not only in the outer layers, it's also in the stellar body. So here you see the minor axis, the minor kinematical axis that is bent and U-shaped, and you also see the major axis with this irregularity. Now, we can model it with a warped disk, but not only, we need to put a kick, a velocity kick to reproduce this U-shaped. And of course, this can be done by combining high resolution observation and very detailed modeling, which, for example, with terrific. And there has been a paper about it recently that you can find here. So let's analyze the tail once again. We already saw this plot, but this is very educational because if you make a PV diagram, you can study how the kinematics work. And here you see a smooth gradient of velocity, which is indicative of RAM pressure stripping, but also this kick in the kinematics from the galactic body. So we cannot explain this with only RAM pressure. Tidal forces must be coming to act. So what probably happened to this galaxy is that maybe a small dwarfs merged, or there was a tidal interaction with it, and disturbed the kinematics. And now with the infall into the cluster, RAM pressure acts afterwards. Now, this is another image of the detection overlay with the optical, because we cannot study only one detailed galaxies. We can try to do more statistics about our cluster and also study the very small dwarf galaxies. And the combination between a deep H1 and deep optical is very important because here we not only detect all the H1, we detect the all and only H1 in the cluster down to this very low mass. But we also have knowledge of the dwarf population which doesn't have H1. So what Dane Kleiner did is to go and see which dwarf galaxies have H1 and which have not. And we see that below a certain magnitude, galaxies do not have H1. So this means that the removal of gas was must happen fast. And we can also make toy models and infer some mass loss time scales. And you can see here that at 10 to the 6, we are on the order of 30 mega years, one order of magnitude lower than at higher masses. And this is let's say, an individual study, but we're also interested in more statistical studies, such as the H1 mass function in the cluster. And we see this collapse. And the significance of these detections is about 40 sigma. So we're pretty sure that here, the mass function is going down. And this is very interesting because we know from denser environments that this would happen compared to the environment, like Coma and Virgo, but this is the first time that we are seeing this in such a less dense environment. I went very fast. So these are our conclusions. The future of H1 is bright. We are going to see so much more investigating this low regime parameter space where you see the Meerkat-Fornax survey here. And if you really want to take two main points, is that in Fornax, RAM pressure and tidal interactions coexist in shaping galaxies, and that gas removal is fast. And this may have lots of implications of also the conditions of the dwarfs and UDGs that we see and how they fit in the scaling relations. So another very good point about this survey and the other Meerkat survey is that it's because of the quality of detailed observations that we are certain of our results. Like we can really do highly detailed investigation of our galaxies. So thank you very much.
Thank you. Lots of time for questions. Okay. I guess.
Very nice talk. I saw you quantifying the gas stripping timescale as a function of H1 mass, but I assume the total bionic mass should also be important there.
Yeah, of course, I refer you to take Dane after in the coffee break to ask more questions about it. But of course, it's also the stellar mass that is insufficient in these galaxies to retain the gas. So there is, of course, this contribution. And about the modeling, we can talk later.
Yeah, sorry. If the people presenting sparklers can start lining up there in the meantime. Thank you.
Hi, Philippe. Thank you. So is it possible to use the information on the density of the hot gas from X-rays together with the density of the H1 from your observation to try to estimate in a different way the time scales of stripping completely gas off the galaxy? Have you been thinking about that, or?
Well, we certainly thought about the interaction between the fact that, for example, if I find the footprint, you see that all the H1 exists kind of at most at the edge of our X-ray footprint. Of course, there are all the projections effect. So it would be very interesting what you suggest to do in a more statistical way and more profiles. But what I always now we are also waiting for the Rosita observations in the X-ray, which will be much more detailed and will allow us to make really a one-to-one comparison with the hot gas in this environment. But thank you for the suggestion.
Hey Filippo, Luca Cortese from ICRAR in Perth. Thanks a lot for the nice talk. I might have missed it, but your point about the dwarfs not being detected, does it mean that you detect all the galaxies in Fornax above a certain luminosity threshold? Because in that map, you have all the early types that are not detected.
Yes. So the Fornax Deep Survey has a surface magnitude limit of 28.4 per arc second. So, and it was a multi-band project that actually has a completeness of about, in the papers, I think, 90%. So this is why we think...
So you detect H1 in all the early types in Fornax?
No.
High masses?
No, not in all. There are also some that also have lost already their gas as early types.
Even at high mass?
Even, I mean, for example, NGC13, the BCG doesn't have H1, for example.
But so you also have non-detections above a certain luminosity limit?
Yes.
It's not only the dwarfs?
Yeah, no, it's not only the dwarf, of course. Maybe.
I actually want to add a question following Luca's question. I'm wondering, could some of these really low mass galaxies, they are assembled to be gas pool, for example, affected by preheating or reionization stage?
I mean, we don't really know how these galaxies actually entered the cluster, so we don't have this information. We know that they are associated to it. So what you're saying, it's also possible that they already didn't have H1 beforehand. But of course, some of them must have lost the H1 within the cluster. And we have also another, not about a dwarf galaxy, but a smallish 10 to the 8 galaxy that is clearly truncated because of its passage through the cluster. So when we go to study individually them, we will find out much more information.
Okay, let's thank Filippo again. Okay, now we have a session with 15 poster sparklers. Do you know which order you're in according to the program? Yes, no? Okay, so what's going to happen is that I'll give you the mic. Your slides will advance every 90 seconds. So please, when your 90 seconds expires, please pass the mic to the next person. So the first one is Patak.
No.
Maybe. Can you go there? Go up there, so.
Okay.
Yeah.
Oh, can you tell me what 90 seconds?
Yeah, your slide will disappear.
Okay, great.
Warning every 60 seconds because it becomes messy.
Yeah. Hi, everyone. I'm Deb, or Devoshmita Pathak. I'm a graduate student at The Ohio State University, and I'll be presenting a poster with 2 key results. So we have new constraints, new best set of constraints on the probability distribution functions. So this is for structure finding in 19 nearby star-forming galaxies, where we see a very consistent 2-component probability distribution function emerge. And if we could go to the next slide. Yeah, and we also look at the diffuse gas in the ISM as well as star-forming regions or H2 regions in these galaxies. And we provide a new set of constraints on the UV direct radiation pressure as well as infrared reprocessed radiation pressure across more than 20,000 H2 regions in these galaxies. And we find that typical H2 regions show IR reprocessed radiation pressure of order 20%, 10 to 20% of the UV direct radiation pressure, but on smaller scales in galaxy centers, for example, so in more extreme regions where the column density is higher and the optical depth is higher for IR, you see
Your
more
time is up,
IR
sorry.
radiation pressure. Thank you.
Sorry.
Excellent.
Hi, everyone. My name is Misima Masipa. I'm a PhD student at the University of the Western Cape. So I'm working on using machine learning models, particularly things such as UNet and ResNet, to automatically detect or flag RFI and H1 intensity mapping data. So I'm using the MIA class LPAN data. So if you look here at the top, you have the flagging that was done using the MIA class pipeline. And on the bottom, you see the flagging that was done using one of the models that I have trained. So if you want to know more about the RFI flagging using machine learning techniques, please come check out my poster. Thank you.
Hello, everyone. So in these galaxies, the thickness of the H1 layer is crucial to understand some of the scaling relations, but also some of the properties of galaxies, such as disk stability, or also the shape of dark matter halo. But usually the H1 in galaxies are considered as a single component disk, although if you have seen Sushma's and Erwin's talk this morning, they're talking about an extra layer of gas, which is called as thick disk. So it raises the questions if a single component is enough to model the H1 in galaxies, and what would be the implication of star formation and also feedback in a multi-component scenario. So trying to answer these questions, we measured the scale height of 4 edge-on disk galaxies from the Mongoose survey, and we find possible evidence for a two-component disk. But if you are interested, my name is Nutaina Renevarmina. I am a master's student from the University of Cape Town, and I invite you to check out my poster at 144, if I'm not mistaken. Thank you.
Hello. Yeah. Okay. My name is Nazir Makta. My supervisors are Rosalind Skelton and Sarah Blythe from the South African Astronomical Observatory and the University of Cape Town. And yeah, searching for H1-rich ultra-diffuse galaxies and low-surface brightness galaxies in the Hydra cluster. So ultra-diffuse galaxies are really extended and faint galaxies. And the reason why we are interested in them is because we find them in dense regions. Quite puzzling. So what we go ahead and do is we use Meerkat to look in the H1 for these galaxies. This is an image in the middle. Oh, it's actually nice. You can't see it. Well, that's the UDG in the Hydra cluster. And we actually observe this in H1. Yeah, I have to check. What did I want to say next? So along with this UDG, we also find other low surface brightness galaxies, and we actually find a cloud, a dark cloud of neutral hydrogen in the cluster. So the main purpose of this particular project is a pilot. So we're looking at the center of the cluster for UDGs. And what we really want to do next is to look for how UDGs evolve from the outer regions of the cluster to the center to see any sort of evolution. So we have now acquired new data up to the virial radius. And so that's the forthcoming project we'll be working on.
Thank you. Okay, so we skip to the next one.
Hello, everyone. I'm Karen Masters. I'm a faculty member at Haverford College, and I wanted to just take a minute to update on what we've been doing for the H1 follow-up for the manga survey. Thank you to Michelle for the advert in the plenary on this. We've been collecting single dish follow-up for every galaxy in manga. It's 10,000 galaxies in total, this large IFU survey. A lot of the sample is to the north of existing wide area untargeted surveys like Alfalfa, although we are folding in Alfalfa and increasingly now also fast observations where they're available. There's some data papers that you can see there, and Dave and I are working on getting data release 4 out, which is almost 70% of the manga sample. Dave was actually also observing last night at Greenbank remotely, and if you could have the next slide. So the new observations that we just got approved for the next 2 years as filler program at Greenbank will actually be to go to deeper H1 limits at the high mass end of this to try to get some consistent gas fraction limits at the high mass end and really get rid of a lot of the upper limits. But that there is the H1 mass stellar mass relation for the current sample. And I just wanted to take a minute to advertise some nice work we've done with this, right? The niche here is that we have IFU data for everything. That's kind of the point. And so Anubhav Sharma was a student of mine at Haverford. We used WISE and manga to identify very low star formation rate galaxies that were H1 rich in this sample and look at the properties. Thank you.
Hello, everyone. I'm Fu Jian from Shanghai Observatory in China. Today, I introduce some of our recent work. It is to simulate the interferometer array for the 21 centimeter signal for H1 gas. And in the last few years, we developed a software. Its name is OmniUV, which can simulate the interferometer array for the visibility data and also the imaging processing, and we adopt the Illustris TNG 100 data for H1 simulation data, but we can also use the semi-analytic model data for H1. Turn to the next slides. Next slide. Yeah, and we combine the configuration data for SK1 mid, and we simulated the full box of Illustris TNG for the H1, and we get here is an example. We show we input a simulated H1 group and get the visibility data, and then based on the visibility data, we processing the imaging processing, and we simulate 2 sets of the simulation with 6-hour integral time, and 6-hour UV coverage with different integral time. And the main conclusion is that with the OmniUV software, we can simulate the interferometer array signal and for both SK and for some future array. Thank you.
Hi, everyone. Now that I have your attention as a fire hazard, I'd like you to try and imagine what resolved H1 looks like at column densities of 10 to the 18 and even 10 to the 17. If you don't know, or if you know what that looks like, then you're probably a Mongoose core member. If you're not a Mongoose core member, then you can come and talk to us and see what it's all about. I've heard a lot about Mongoose. We can boast that we're the deepest, most resolved H1 survey in emission, which is fantastic. I'm particularly interested in the close nearby interacting systems. I've been studying the gas, both the different densities. In particular, it's been tapping into a very specific range of tidal fields and how that affects the gas outside the disk. So I've been looking at how that affects the diffuse component, but also what happens if we can see traces of that inside the disk itself. So if you're interested in this kind of tomfoolery, come find me or some of the other Mongoose members. Thanks very much.
Thank you. Cannot hear you. Yeah. Can you increase the volume?
Hello, my name is Dejani Zode. I'm a postdoc at Northwest University here in South Africa. So I'm working on H1 detected Phoenix galaxy members. So using SALT observation, so we try to measure the H alpha in each Phoenix members. We try to measure the H alpha and try to see the star formation history of the Phoenix galaxy members. So my poster session is tomorrow in the afternoon. Please check out my poster at 28/7. Thank you.
Thank you.
Hello, everyone. I'm Junaid Townsend, a PhD student at the University of the Western Cape. And my poster is on studying the H1 content of the local universe using a technique known as intensity mapping. Next slide, please. Thank you. So in particular, we use data from the MIGHTY survey and apply what is known as the delay spectrum technique to on the measurement sets in order to estimate the power spectrum, and then likewise compare that to a catalog of H1 galaxies that were detected using the same data and compare the power spectra of the two. And one of the reasons we do that is to test the robustness of the intensity mapping technique in the regime where it is possible to make direct H1 detections of galaxies. If you'd like to learn more and discuss some of the details of this project, please come and have a look at my poster tomorrow. Thank you.
Thanks.
All right. Hello, everyone. My name is Karina Santana. I am a PhD student at the University of Witwatersrand, supervised by Roger Dean and Dr. Philippe Mbachani. And my poster is about meerkat observations of two nearby late-type galaxies, which offer new insights into accretion and AGN feedback with neutral hydrogen. So our first galaxy is NGC 6240, which is an archetype post-merger system. So with Meerkat, we get, or thanks to Meerkat's image fidelity and sensitivity, we see for the first time H1 emission in this galaxy. We've got two clear planes of H1 emission, the primary plane and the southeast plane that is extending towards the neighboring galaxy. This is evidence of first time having like an interaction, or first evidence for the interaction with this neighboring galaxy. If we zoom in, we're actually able to spatially resolve certain H1 absorption components. And then zooming out, radio continuum work done by my colleague Isaac, we have a discovery of a 15 kiloparsec shock front just beyond the virial radius of this galaxy. The second galaxy, if you go to the next slide, second galaxy is NGC 5643, which is a nearby Seaford 2 galaxy. Looking at the H1 emission, we see that it's like a northern extended tail. Then looking at its kinematic, its disk is regularly rotating, but the tail is counter-rotating and extending well beyond the systemic velocity of the system. We believe that the tail is likely falling onto the disk from the intergalactic medium, but we can discuss some more tomorrow afternoon at my poster. Thanks.
Thanks. Is Mark around? No? So let's skip to this next one.
Hi, everyone. My name is Paul Andaliso. I'm a PhD student at University of Witwatersrand, supervised by Professor Roger Dean and Professor Ed Elsin at University of the Western Cape. So in my post, I'll be talking about how we're using Meerkat L-band observations of the X-ray luminous galaxy cluster Abel 3408, and how for the first time we're actually modeling the dynamics of the galaxies within this cluster using a uniform pipeline that is based on Piper-Roller. So this really beautiful plot I'm showing here is H1 intensity map of the galaxy cluster showing 64 detections observed with the Meerkat. And the gray circled detections are the WISE counterparts. The galaxies that are modeled, I'm showing them with the squares, and some of the galaxies are not modeled due to signal to noise ratio. So if you really want to know more about this, please visit my poster. Thanks.
Thanks.
Good afternoon, everyone. My name is Luan Lekwebushe. I'm a PhD student at Rhodes University. So my project is focused on studying the H1 content in the Sharp supercluster. The Sharp supercluster is the largest supercluster in the local universe. It is located in the southern hemisphere. It has approximately 25 apple cluster plus groups. Multiple band studies have been undertaken in this cluster, but there's still a lack of H1 studies in the cluster. Because of capability and the high sensitivity of Meerkat, now we can be able to study the H1 content in this cluster. So far, 2 apple clusters have been observed using the Meerkat as part of the Meerkat Galaxy Cluster Survey Legacy. So in this figure there, I am showing the Sharp supercluster with all the clusters inside of it. And then on this side here, I'm showing the scaling relations that we've undertaken using the data at hand. And we compared our scaling relations to different environments to investigate the environmental impact on the H1 content of our galaxies. So if you're interested in this project, you can visit my poster at the poster room so that we can discuss the current work that we're doing and the future work that we're planning for this project. I thank you.
Thank you. Should we listen to the recorded one? We don't have questions for the poster studies.
For the next sessions, I can get on.
Yeah.
Okay.
Okay, so let's thank all the speakers in this session. The wonderful poster sparkers. Please go and check out those posters, and also a big thanks to the helpers and the technicians on the back. Andrea, how are you?
I'm doing good, thank you. How are you doing?
Good, thanks. So when did you get here?
I got here last night, actually.
Okay.
Thursday, so I started Friday. Yeah, but I hadn't made it to any talk until this morning, so because I'm just so busy having conversations with you.
Yeah, I mean, that's the main reason why you come
I
to
know.
this kind of conferences, right?
Yeah, yeah. How are you? How are things? I think I haven't seen you since you became PI of all of these. So congratulations.
Thanks. Yeah, it's so good. I mean, busy. Wallaby and also Luke and I had this nice news program. He's a lot of fun. Move. We are
Yes.
processing the data and
Oh, okay.
so it's
Did
basically
Laura that's you?
she approached me, she sent me the slides
Okay.
tomorrow.
Yeah.
And I think it's good to
Okay.
I guess it's interesting there is such a lot of information rights, so maybe just
I
might be real, might be the way we measure things that is not the same. So
I was
it's
one.
not,
I saw the slides last night, and I suggested checking the make sure the IMFs are consistent, which is all.
yeah, you know, all those kind of
So,
things
which
can
could,
add up.
which could either make things closer or make things farther away, depending on which way things go.
But yeah, we can try to understand selections.
Yeah.
She might also compare with Isaiah, that is maybe more similar sample, but we see.
Yes, that's true.
So it's because those have a higher transformation rate measured same way as X gas. So
Yeah.
it's great to see La Duma
Yeah.
results and
Yeah.
very excited about it.
Yeah. No,
And I was telling Sarah that we should have some more regular catch-ups.
Yes, yeah.
Now that you know.
Things are happening. Yeah, I think the different papers are moving in different speeds.
Yeah, but that's always the case.
Yeah, yeah.
Oh,
so there he is. There he is. We need to me and you.
Can I give you this back?
Yes, please.
Thanks a lot for your help.
Yeah, me and you. Yes.
The bag.
Yeah.
Excellent.
Yeah. It'll be interesting to see if it doesn't. Yeah.
Excuse me?
job. You know so much more.
Sorry about that. I should have came and gave it back. I'm gonna just.
I was following the wrong.
will be
To run the other one.
I'll hand to him. Yeah, then you can assist you. I'll instruct him to grab your mic from you as soon as you ask the question, and if there's someone in this row, and then he'll come and collect the mic from. Is there somebody else on that? Yes.
That's
Let's see.
Let's go.
Okay.
Hi, everyone. Welcome to the last session of the day. And so we've got 5 talks, starting with an invited talk from Mario Santos. So just an announcement, as a reminder to the speakers, when I give the speaker a 5 minutes warning, if you're the next speaker, please go and get mic'd up. And as usual, please introduce yourself before you ask a question. I'm Bradley Frank. I'm from the UK ADC. And yeah, speakers, please keep to time. Thank you very much.
All right. I thought there was like a screen here as well. All right. So I would like to, oh, it's not on. I'd like to first thank the organizers for the invitation. I mean, the title of the symposium is H1 in and around galaxies. And I'm talking about H1 everywhere, and in particular on very, very large scales. Can we have a breakthrough in cosmology in the next 10 years? Probably not, but but if we have, then you know, wide redshift surveys will probably play a role in that, and in particular, you know, the optical near-infrared galaxy redshift surveys, you know, the ones that we hear about a lot, will definitely contribute to that. But in the radio, you can also use the H1 21 centimeter line as a galaxy redshift survey. It's a great tracer from dark matter, very easy to get redshifts from the radio. Unfortunately, you know, the line is a bit weak, so it's, you know, quite time consuming. So even if you have like 10,000 hours with the current setup of the SKA, SK mid, and you can cover a few thousand square degrees up to, you know, below redshift 0.5. And I know that you can do, but you know, it's still great, but won't be enough for like competitive cosmology. And so this is where the idea of H1 intensity map, neutron hydrogen intensity map came about. So I should say that every time you do an image in H1 of a galaxy, like that nice one, early one from Meerkat, you are doing intensity mapping. The difference for cosmology is that, so when we look at the H1 line, instead of trying to detect every single galaxy here, you know, in space and angle and redshift, and then do statistics with this, we just look at integrating emission from all these galaxies, and you make these diffuse maps, these low resolution maps, these blobs. Resolution, but it's still good enough for cosmology, and then we can just look at the power spectrum, and that's how we can do intensity mapping. So that's the idea, and of course you get very high resolution in the radio. Now, both SKA and Meerkat were not designed as intensity mapping machines. They are facilities, but they, you know, we can use them for that. So if you use the interferometer, you'll be probing the small scale power spectrum, the H1 power spectrum on small scales, so like clusters and subcluster scales. If you want to probe cosmology, these real large scales above 10 megaparsecs, then you don't have enough short baselines for that. And then what was proposed is to use the single dish observations from these arrays, just single dish data, and map the sky using that for these large scales. So again, it's low angle resolution, but this provides you extremely large survey speeds. The simultaneous noise really, from this point of view, is absolutely amazing. And then you still get all the nice high spectroscopic redshift resolution. So, you know, it seems like great, at least on paper. And so for a few slides, I'm just going to, so before jumping into cosmology, I'm just going to talk a bit about what we have done with interferometer, because I think it's probably more appealing to the crowd here doing like an H1 galaxy stuff. And so we looked at Meerkat data, public data, and at the time, the deepest pointing there was this 1 hour pointing, 100 hour pointing, we call the deep to field. I think even now, the deepest pointings after this is just the Laduma pointings. I'm not sure if there's anything else. And so we decided, okay, let's try to do this H1 intensity mapping with this. We did all the calibration, etc. You know, you can see the continuum image here. All right, so what to do next? That's a bit different from the usual, which is we didn't try to look at an H1 cube from this. So usually do try to do the continuous subtraction like an H1 cube. Instead, we look straight at the visibilities. They've been in the UV plane, and then we do a Fourier transform along frequency. This is called the delay power spectrum. And well, for those that are involved in this area, you can see that actually this is like some of the cleanest power spectrum you get from this technique that are in the market for sure. Now, when we did this, we still found that there was a slight bit of contamination there that it turns out to be related with some of the Meerkat baselines at really, really low level contamination. So we were able to flag that and get the nice clean spectra you see on the right there. Now the very red stuff you see here, that's just a continuum contamination. So in terms of an H1 cube, this will be like removing that bit there is like doing a continuum subtraction. It's kind of equivalent to that. So you take out the parts there that are clean, and we got a power spectrum from that. At these two reasonably high rate shifts, this was done in the L band. So this is an H1 power spectrum, H1 intensity mapping power spectrum at these two rate shifts, the one-dimensional power spectrum. And in blue, that was the possible region we had in terms of theoretical models of where we thought the signal would be. So it was quite wide. There was a lot of uncertainty. So you can see how these measurements really help to constrain these. And I do think this is a very interesting window to explore. Again, if you're interested on cluster and subcluster H1 science, it would be great to compare these measurements with simulations. And actually, once you have enough sensitivity, you can also compare these measurements with simulations. And yeah, I mean, it's a great complement to stacking as well as you go to higher rate shifts. And you actually don't need an external galaxy catalog to do this. So, just keep that in mind. I mean, I should say this is the only claim detection so far. Some people are still not completely convinced that this is a pure detection that we are accumulating more data to analyzing more data, I should say, to get to this. And in particular with the MIGHTY survey, I just want to say that what we've analyzed so far with the MIGHTY survey is not sensitive enough for the detection, but we were able to set upper limits, and the upper limits are consistent with our previous measurements. And you can see the poster by Junaid Townsend a bit more about this. Okay, now I'm going to move into the cosmology side of things to the single dish approach, which is very weird for people that are used to using interferometers. And to do that, we started this wide survey called MeerClass, the Meerkat Large Area Synoptic Survey. And the goal is really to cover all the southern sky with this single dish intensity mapping survey. And this will be overlapping with plenty of spectroscopic data. You see some of that data mentioned there. In particular, we're really hoping that the foremost survey comes along to help with that spectroscopic coverage. And so this will be observed outside the galaxy. We don't really like the galaxy because of contamination. And so far, we observed about 380 hours in the UHF band. And that what you're showing here is the footprint of that service so far. We just finished observing like yesterday. So the ultimate goal will be to achieve something like 2,500 hours over the 10,000 square degrees area of the southern sky. And we'll be producing continuing images at the same time, and that should give you a roughly a 30 microjoules RMS in noise and 13 arc seconds resolution for the continuing images. So that's kind of the status here. These are the forecasts for the full survey. So with H1 intensity mapping using this single dish low resolution mapping of the sky, the first goal is to measure the H1 power spectrum at several rate shifts.
So from 0.4 all the way to 1.2, and we'll be able to do that quite well, in particular on these very large scales, and that will allow for some interesting constraints on primarily non-Gaussianity when you cross-correlate with surveys like the LSST. We should be able to measure the barrier acoustic oscillations at a few redshifts, at least at the ones below redshift 1. So that's also quite interesting. And this will provide constraints on the Hubble rate across redshifts. What I'm showing here as well is the cross correlation. We can get this information just from the H1 power spectrum itself, but we can also cross-correlate to these galaxy surveys, and that will help also to disentangle some systematics. So there's showing here constraints that you get by cross-correlating with DESI, foremost, and then Euclid at higher redshifts. And the same for the growth rate that is taken from redshift space distortions. All right. So, okay, that's the nice part. The issue here is that the signal to noise is quite high with this survey. The problem here is the contaminants. The contaminants can be much higher than the noise itself, and that's an issue we need to deal with. All this stuff that adds up, I've kind of listed here in red the ones that worry me the most. I can say that actually the one that's been worrying me the most is RFI, which is not what initially I thought would be worrying me the most. And I'm showing here on the left the band we see from the L band at the Meerkat site. You see lots of contamination from satellites and so on. The UHF band actually turns out to be quite clean, and not as clean as you see here. There's some spikes once in a while, but most of the time it's like that. But you still have this very large contamination at 950 megahertz, which is the cell phone towers that are kind of around the site, and they kind of problematic. And I have shown one example of that at the top here, which the signal sometimes is so strong that just moves the whole system non-linear, and then you get these weird effects, and then you need to deal with that. So that's kind of a big issue. And just to say, just because last week there was a lot of discussion about satellites, we did recently published or submitted a paper about doing satellite simulations and calibrating that using the Meerkat data we have. And you can see actually in that figure, one is the observation, the other is what we get from the Meerkat simulation. The goal here is to see if we can really fit these at the level where we can probably start using these simulations to remove some of the satellite contamination as well. All right, so just moving into the survey itself. So we had to develop the pipeline from scratch because it's like single dish. And so the peculiar thing about this survey is the scanning strategy. So the dishes are fixed at constant elevation. They are all pointing in the same direction. They're moving very fast back and forth. It's like a Meerkat should be doing, right? Scanning the horizon. And so basically in, say, 1.5 hours, you cover about 300 square degrees of the sky. So it is a very fast survey in that sense. And then you go back, do it again, try to get a nice cross matching, and that helps a lot with the calibration. We're also doing noise diode injection that helps to stabilize the gain over time. Although I have to be honest, the Meerkat gain is quite stable over time already. And the fact we're scanning this fast allows us to have these measurements over large angular scales without extra instrumental fluctuations. So that's kind of the idea. All these things moving back and forth, and then we make maps. So now we're taking data from every single dish. So every single dish can make a map of the sky. We can just add all those maps together. And what we see is this very nice map of the galactic synchrotron. So if you want to do galactic science, there's lots of data for that. And you can see the comparison here. The top is actually the model, and the bottom is our data. And you see they kind of match quite well. Once you remove the galactic synchrotron, you see here on your right this contamination that's coming from point sources, very strong point sources on the field. Now, next step here is foreground cleaning, and our approach was a PCA cleaning to do that. This is, for think in terms of an H1 cube, this is equivalent of trying to do like a continuous subtraction of the H1 cube. We found that the principal component analysis approach performed the best for this. We need to deal with signal loss and so on. So, that's an important issue, but so far it seems to be working well. So we kind of reached the noise level by doing this. And what we did next, so now we have like this kind of H1 cube, this low resolution H1 cube. And so what we do next is we cross-correlate that H1 cube with a galaxy survey, in this case, the WiggleZ galaxy survey, and we got a power spectrum measurement. At the time, this was the first cosmological result using Meerkat. And so this power spectrum you see here, it's the H1 power spectrum cross-correlated with the WiggleZ galaxies because they do have, these galaxies also have H1 in them. But they're actually both tracing the underlying dark matter field. And you can convert these measurements into several types of constraints, including the total H1 density of the universe at those redshifts. And I invite you to, see Martha's talk next because she'll add a bit more about this. So right now we are really focusing on the UHF band. This is really our goal at the moment. We've already observed a big chunk of the sky, something like 2,000 square degrees around the equator, because we're just trying to overlap with DESI and other data sets. And I wish I could show you a bit more from this. Unfortunately, it's not ready for public eyes yet. I can just tell you that the spectral behavior is quite nice. And we have this, I'm showing there the redshift range, and this is the actual signal. Well, it's mostly synchronous seeing there. What we have available after RFI flagging compared to the blue bit, which was what was available for our cosmological redshift range with the L band. So yeah, I'll stop here. Just one last slide, because I did mention this, that we are doing at the same time the continuous imaging. And this was done recently with one of these scans. This is a single scan, and we just cover this area of the sky. And you can see more about this if you check the poster by Suleiman. So, okay, I'll stop here. We'll see a bit early, but thanks a lot.
Thank you very much. So we have time for a few questions.
Andrew Baker, Rutgers. Mario, for those of us who don't do intensity mapping, could you just kind of roughly give us an idea of the figure of merit? What's the ideal survey? How does area versus depth versus galactic latitude kind of trade off in terms of getting to the results you want?
Well, for cosmology, it's, it depends on the instrument as well, right? So, but for something like for instance, for the SKA, the more area, the better. So, if you should cover as much as you can outside the galaxy, and that's maybe 15,000 square degrees. And then, with the integration time for that will be, around the 5,000 hours, or maybe a bit less now, depending on. But it does depend on how deep you want to go in redshift, right? There's a big range on that. For the interferometer side of things, at least with MIGHTY, we found that something like 100 hours per pointing, it's kind of where we want to be, at least in the L band. Probably with the HF band that would be different, and then you should ideally then combine different pointings to increase the cosmic variance if that's an issue.
Mario, thanks. Very nice. Fernando Camilo from Soraya. A quick question. Can you tell us more about what this gives you that you don't get from DESI and Euclid and so on? Speak a little more about what do we really get from these types of surveys? Thanks.
Yeah, just the fact that you're using a very different tracer does allow you there's always going to be systematics at the level of these galaxy surveys because you're doing it's so deep that you're going to have issues. So the fact that you can course correlate that just from cosmology, that's already quite interesting. But on top of that, because the H1 and say an optical galaxy survey, they trace the dark matter field with different biases. Then you can, by combining that information, you can actually basically break some degeneracies for some of these cosmological parameters, like the growth rate in terms of Ricci space distortions or primordial non-Gaussianity, and that's something you cannot do with a single tracer alone. And H1 is a very different bias from optical galaxies, and so that really helps a lot in that. So I'll say break contamination for both surveys, and then add this ability to break degeneracies in cosmological parameters by combining that. So that we are in the field of high precision cosmology, and these systematics are going to become a big issue for any type of survey.
Okay, well, thanks a lot, Mario, for a great talk. And I encourage you to speak to Mario after the talk if you have any more questions. Next speaker is Marta Spinelli.
Thank you. Thanks for making the last session. So my talk today, is it me changing? Oh, okay. So my talk today is very much in line with what Mario has just discussed. I guess it's a second opportunity to convince you of how cool it is to do cosmology with H1 and why we should definitely do it despite all the challenges. This is a very new measurement, and I think it's really something we should push for. First of all, who I am, I'm Marta Spinelli. I'm a researcher at the Observatoire de la Côte d'Azur in Nice, in France. But I've been spending here some of my postdoc. I was working with Mario before, and I kept working with the UWC team and the MIR-class team since a while now. So first slide of my talks have nothing to do with the talk, just some friends ask me for a favor. So especially you, if you like visualization of H1 data, please check the booth for the IDEA Visualization Laboratory. Lucia Marchetti is there with her team to help you and work you through this. So sorry for this, but now I go back on H1 and why it's interesting for cosmology. You have heard this from Christine this morning, but I want to stress how important is H1 in the whole history and evolution of the universe, really from when the CMB has been released, because neutral region has been formed through cosmic dawn, all the phases of reionization, and all what in cosmology we call the late universe. So in the late universe is what in cosmology we define everything that is after the end of reionization. And there is where you clearly see the Lasky structure, is where neutral region is a clear, even if biased, tracer of all the structure and how they evolve through redshift. So this is where the SK is so important for us, because if we want to see the Lasky structure up to redshift 6, we need an instrument that can do that. And we can indeed with the SK mid reach with the redshift 21 centimeter line up to redshift 3. And this is quite amazing because all these surveys that also Mario mentioned, the galaxy survey, they do not, all of them reach this type of redshift. And then we can even go further and combine observation intensity mapping from SK low and go really to the end of reionization in entering a territory that galaxy survey can really not touch. So this is why this is really important to pursue. And I just want to mention that to do this type of observation that are new, you need to arrive prepared, you need to construct pipelines. And these pipelines cannot be constructed if you don't see the challenges that the data are offering. So it's really, really important for us that we have MIR-CAT data, that we are working with MIR-CAT data, and in any case, we can really reach redshift 1.5 if everything goes well with this observation, and this is super important for the field. So something that I think is related to some of the questions have been asked. Here we are looking for the dark universe. We are trying to answer a question about how the universe evolved and what is the role of dark matter and dark energy in all this. But we are actually looking at H1. So it's super important for our community to know things about H1, to learn things about the bias, how in general the halos and H1 galaxies are related. Because these are things that are important to go down in constraint in the errors of the power spectrum. So why we like so much the power spectrum and why we like so much this cosmological parameter when we talk about cosmology, why we like matter clustering so much, for example? Well, because in matter clustering, there is clear information of all the cosmological model that we want. And here is just like a simple simulation to show that if my cosmological parameters, for example, are low in sigma 8 and omega m, so the density of matter is low, and it's much very different from a case where the matter, for example, density is high. And you see the clustering changing so much. So there is a lot of information that we want to extract from here. But as we were saying, even in the talk from Mario, that what we see is actually H1 in galaxies. And these trace the dark matter, not perfect way. It's something that we need to understand. We cannot, as we said, measure each of these H1 galaxy. We are talking about redshift 6 here, redshift 3. So this is something that you can not do resolving single H1 galaxies. So you can do with this intensity mapping technique that you just discussed. You lose a bit of resolution and you end up with something like that. The good thing is that you can use CMB developed tools to analyze this type of maps, because it really looks like a large scale structure map similar to when you measure the fluctuation of the CMB. But the good thing here is that it's not at one redshift. We have really a tomographic view of our universe, because we can span all this redshift range. So this is super important if you want to learn about how the matter evolves, and so about dark energy, for example. And so it's this tomographic view of the universe that can be really game-changing. So where is the information? So here I just want to state again, so the first thing we want to measure is this 21 centimeter power spectrum. So the reason why we are so interested in it is because it maps the matter power spectrum. And there are some coefficients in front that are related to what we know about H1 galaxies. So the total H1 densities, for example, or the bias of H1 galaxies. This is why I think the communication between the cosmological community and this community is super important, because we need to really pin down this coefficient in front to go to the matter. And so this is a forecast done with MCMC. If we measure this 21 centimeter power spectrum, what we can learn about the cosmological parameter. So the constraints that we can get on each cosmological parameter is really good and complementary to other survey. This is something that could be new with the new tracer. This is also to answer the previous question. And this is really something that we need in cosmology to achieve this type of precision. And since we still have some systematic in our data, Mario has shown how difficult it is to do this measurement. There is a safe strategy that is to kill a bit the systematic cross-correlating with galaxy survey. I'm going to discuss this a little bit more in a second. And so what you're going to measure in that case is not the auto power spectrum with the 21 centimeter emission, but you're going to measure now the cross-correlation between your 21 centimeter cleaned map and the galaxy survey. So this helps reducing the systematics. And indeed, you can expect to get a constraint that are, if you assume you know the galaxy part, that are more or less comparable with what you get in auto power spectrum. A bit less. Here you can see the difference between the green and the magenta, and the auto power spectrum and the cross power spectrum. What is this large, not very nice constraint in yellow is when we assume that we know nothing about the H1 bias and the temperature brightness in front, so the omega H1 in the end. And so you see that these, what we call nuisance parameter, really reduce the constraining power. So having measurement of the bias and omega H1 really improve our constraining power. So as just to give you an idea, this is just a proof of concept, but we can try to use this pipeline already with the data that we have. And of course, you're not going to get like very nice constraint at the moment. But if you look up there in that dashed lines, these are with the data, the actual detection of data that we have, and you can start seeing that we can actually make a measurement of the density of cold dark matter. I think this is really amazing. It's something, this is just a proof of concept plot, but we are working towards having really a significant detection of this type. So the data that have been used here are the data that Mario also discussed. This is our 2019 campaign, that the first one that we managed to calibrate. So we have this 7.7 sigma detection in cross correlation with Wiggle Z galaxies. And also, of course, this is the start of a development of a very complex pipeline where RFI flagging has been improved day by day, and also all this concept of foreground cleaning. So let me just pass a second on what is this foreground cleaning thing. As Mario was saying, we need to find algorithm similar to the case of the CMB to separate what are foregrounds that are much order of magnitude higher than our signal, and the H1 cosmological pure pristine signal that we are looking for. So here, for example, you see the difference. It's like the synchrotron emission is at a Kelvin level, like tenths of Kelvin level, while our signal is millikelvin level. So there are several techniques to do that, all, as I was saying, some of them at least imported from EOR or CMB. And we did a blind data challenge similar to what the SK has been organizing. It was a group of people involved in that. The results are quite nice. We have constructed a mock realistic data set and tried several methods on that. The results are that if the systematics are too complicated, we start struggling a little bit. So we need a bit more to dig down a little bit more on this. So here is supposed to be all white, but you see there are residuals. And then you can just to have a look, compare the performances of the various foreground cleaning methods. And in some region, they behave well, in some region, no. So it's nice to have all of them and to compare them. So now we have more data. So we really getting more data. As Mario has shown, we are covering a large patch in the sky in UHF. We have all this data already available. We hope to have more data in the future, so to reach this very large area in the sky. So this little black square there, and yes, we have all this superposition with all these galaxy survey that can be super useful for systematics and cross correlation and kill the systematics. So this little square there is an L band, and is our 21 result, L band 2021 results. So we really managed to get also a detection in cross correlation. This is the deepest single dish H1 data that we have up to now. It's really nice. Even if our superposition with gamma is very small, we still have managed to get a cross correlation detection similar to what we have discussed with Wiggle Z. And this is impressive because we don't have a lot of gamma galaxies, so it really means that the signal is there. But more than this, with these deep measurements that we have, we can start playing and arriving at the level where we would like really to reach an autocorrelation detection, so without the need of using galaxy survey. And here, this is just a preliminary plot that tells you that we are not far from the level expected, that we hope to be at least a large scale. This would be the first measurement at these large scales, higher than the noise, so we are higher than that red line. And this is done with all the survey together. But what we can do, hopefully, is to, what we are trying to do at the moment is to cross-correlating different parts of the data that we have, so different blocks, different sets of antennas, because we're using the antennas in single dish, so we have a lot of signal to noise, and then get a detection cross-correlating, so reducing the systematics in this way. So my last slide, it's a bit open to other things in cosmology that are interested, especially in the era of the SKA. So intensity mapping, of course, is my favorite, and I think it's really important that we have Meerkat data, and we are using this to develop our pipeline. There's also, of course, synergies. We need to cross-correlate with the galaxy survey. We have also cross-correlation results with Planck. Combination result with Planck. We have a part of the science working group, Anastasia is part of it, that are trying to get communication with the H1 science working group and get cosmology for galaxy. I'm done. And then we have continuum Wiggle lensing. So this is, if you're interested in any of this subject, please contact us. And these are the link that I leave on the slide for you. Thanks for your attention.
Thank you so much. We have time for one question.
Thank you very much. Great talk. I'm Céline Pirou from the European Southern Observatory in Germany. I wanted to ask, there are multiple simulations of dark matter only and including bionic physics that show that on small scales, at large K values, bionic physics starts to play a role in this power spectrum that you are showing us. So do you have a sense where this may come into play when we talk about H1 in particular?
So for this type of course, we didn't check this at the level we should check at the moment where we really have nice data. But let's say at level 0, our beam is very large. So we don't see the scales where really you start seeing the difference between baryon physics. So as a first approximation, the large scales are like what you get right normally in a lot of simulation. A lot of simulation agrees on what is happening on the large scales. So we are for the moment kind of safe. When we're going to start getting results, you want to know the details. And so this is why it's important that our community also talks with the simulation. We are trying to get simulation people in and try to make the community understand that we need small physics, but we need large volume, because this is what we are trying to measure here. So it's difficult to find the right balance, but yeah, it's a good question.
Okay, let's thank Marta one more time and welcome our next speaker, Matthew Coles.
Well, thank you very much. I'd like to tell you about peculiar velocities and cosmological constraints from H1 Tully-Fisher surveys. And this is work that I've been doing with my student, Paula Bubel, also Khaled Saeed at the University of Queensland, and Lister Staveley-Smith, who's in the audience, from the University of Western Australia. So cosmological constraints come from peculiar velocities because peculiar velocities are a direct result of the density fluctuations. That means that redshift surveys and peculiar velocity surveys are highly complementary. They're telling you two different ways about the same things. Now, of course, this is the difference between theory and practice. In theory, there is no difference between the two, and in practice, there is. And that's why it's incredibly valuable to do both types of surveys. Redshift surveys are easy, of course, but the hard part with a velocity survey is you need to measure distances independent of redshift. That requires a precise and robust redshift-independent distance indicator. And here we're going to be using the H1 Tully-Fisher relation. Once you've done that, however, there's a lot of really interesting things you can do. For example, you can look at the bulk flow in spheres of a given radius and compare how that looks compared to the prediction from your favorite cosmological model. Or you can look at the growth rate of structure that we've already been talking about in this session. And you can, that tells you both about sigma-8, the amplitude of the fluctuations in the mass, and also about the growth rate of structure or the growth index of structure, which tells you about whether you've got general relativity or some modified theory of gravity. And you can do this both measuring it from peculiar velocities at very low redshift or from redshift space distortions at high redshifts. So again, two highly complementary methods, one direct from the peculiar velocities and one from the redshift surveys. So the work I'd like to tell you about is this, based on this paper by Paula and ourselves. And what we're really doing here is we're reanalyzing the alfalfa H1 Tully-Fisher data in the Cosmic Flows 4 data compilation. And this is really a warm-up for doing the same sort of analysis with the much larger Wallaby data set that I'll be telling you about soon. So Cosmic Flows 4, the Cook et al. Papers in 2020 and 2022, used a two-step method for getting distances. And this is a little bit awkward because first you have to calibrate the Tully-Fisher relation on a subset of your galaxies in clusters, and then you have to apply that same relation to all the other galaxies, including those in different environments in particular, in order to derive the peculiar velocities. Instead, what we're doing is to fit the Tully-Fisher relation and the peculiar velocities simultaneously, using a velocity field model that we've previously reconstructed from a redshift survey. So if you do that, and I haven't got time to go through the whole process here, but just to show you the results, then you find that you're fitting the Tully-Fisher model parameters here, this set of 5 parameters, and then another set of 4 parameters, which are the peculiar velocity model we're using, which is a scaling of a velocity field from the redshift survey plus a bulk motion due to tidal effects from things outside the volume of the redshift survey. And if you do that, then you can use both the CF4 data with the SDSS I-band data or the WISE W1 band data to get two different Tully-Fisher relations. But of course, they both have to reflect the same underlying peculiar velocity field. And here you'll see that the beta parameter is in very good agreement between these two measurements at around 1 sigma. Remembering that the beta, the velocity model scaling, yields the growth rate of structure because F sigma 8, the growth rate and the matter fluctuations are equal to beta times the fluctuations in the galaxies that you can measure from the redshift survey. When you do that, what you find is that the residual motion is in very good agreement with the predictions from, or the measurements and based on the velocity field from a whole bunch of previous work. So we're all getting answers in the same part of the sky, and that part of the sky is not random. It's actually in the direction somewhere between two very large superclusters right at the edge of our velocity field sample. Our redshift model has the Shapley cluster at 14,000 at its edge, and just beyond that at 17 to 18,000, the Vela supercluster. So when we do this, we can look at our growth rate constraints, and we can compare this to what you would expect to get from Planck. So here on the left in this diagram, all the dots to the left of a redshift of 0.1 come from peculiar velocity measurements of F sigma 8, and all the dots to the right of that come from redshift space distortions from various redshift surveys. And this is a log redshift scale, and it emphasizes the lower velocities because I'm talking about peculiar velocities, so I want to talk about low redshift, but it also shows where the biggest deviations are in the growth rate itself. So the purple line shows you what you predict based on Planck and general relativity. So if you have a Planck sigma 8 of 0.81 and GR's growth rate index of 0.55, then you get that purple curve. And you can see that all the data, whether it's right or wrong, whether it's biased or not, does prefer to have a lower F sigma 8 than is predicted by Planck. Now, the Wallaby redshift survey is going to do this all again, but with a much bigger sample. Whereas we had a few thousand redshifts and peculiar velocities with the CF4 sample, with Wallaby we're going to have 500,000 galaxy redshifts and Tully-Fisher peculiar velocities for about 50,000 galaxies. That means about 10% of the Wallaby H1 detections will have suitable inclinations and signal to noise for measuring Tully-Fisher. And you can see that we will cover most of the southern sky, and we will also go out to significantly higher redshifts than was previously the case. And when you do that, and you analyze a mock version of the Wallaby sample and compare it to what we get from Cosmic Flows 4, you see that the Cosmic Flows 4 constraints in purple are much larger, and you do very much better with the constraints from Wallaby with a 10 times larger sample shown in green there. So what do you get then if you go further and you not only use Wallaby, but you also look at the 4HS survey, which Michelle Kluver introduced, I hope most of you to, this morning. So remember, Wallaby is 500,000 redshifts and 50,000 distances from Tully-Fisher, covers most of the southern sky, and it's already happening. We already have the first few thousand galaxies. 4HS is the foremost hemisphere survey. It's going to have something like 6 million plus redshifts and about 500,000 peculiar velocities from the fundamental plane. And it too will cover the whole southern sky down to within 10 degrees of the galactic plane. And it should start in the second half of next year. And when you do that, you get very much tighter constraints on the growth rate forecasts. And very strangely, the predictions have all disappeared off my plot in this version. I'm not sure why. They should look very similar to those predictions there. So imagine those points on my graph. They were there when I checked it this morning, and they've now disappeared. You can go further, of course. You can take these Wallaby and 4HS peculiar velocities, which together will be more than 500,000 peculiar velocities over the whole southern sky. And you can combine them with the DESI peculiar velocity survey in the north, and that will give you about 750,000 peculiar velocities over most of the sky, north and south. And that should provide a 5% precision estimate of the growth rate in bins of redshift of 0.05 out to a redshift of 0.15. And furthermore, if you then add in the DESI and 4HS redshift space distortions, you should get a growth rate out to a redshift of 0.4 and really stringently test lambda CDM and GR. And the thing I want to stress here is not that any one of these surveys is going to do the best job, but that you want to do all of them. You want north and south because you really don't want to be just looking at half the sky. You want both Tully-Fisher and fundamental plane because they each have different systematic errors, and you want to have independent ways of checking these things. But in the next 5 years, I expect we're going to have some spectacularly strong constraints on the growth rate of structure and on things like the bulk flow in spheres of a given size. All right, so before I finish, I want to advertise two things. The first thing I want to advertise is this paper that came out in the last week or so, which is Paula's second paper based on this same work. And it's on an improved Tully-Fisher estimate of H0. And here we take the CF4 data. Here I'm showing the I-band data on the right. The top plot shows you the Tully-Fisher relation for that CF4 data. And then the inset shows you the various primary calibrators that we used in order to fit those directly to get the H0 value. And this is the H0 we get. We get 73.3 with a statistical error of about 2 and a systematic error of around about 3.5. But if you look at the residuals from that relation, you see that's plus or minus about 1 kilometer per second in very many bins over the range that we're covering here. What we're limited by on the statistical error is the small size of that calibrator sample. It's just Poisson errors on the calibrator sample. And then the systematic errors, of course, are the uncertainties in the primary calibrators. So Tully-Fisher is standing ready to do a superb job of measuring H0 once we can sort out those primary calibrations. And then my very last slide, I just want to advertise one more thing. For those of you who are interested in peculiar velocities and cosmic flows, there'll be a workshop on this in 2025 in February at Brisbane, Australia. Please do take note of that. More advertising will come for that soon. Otherwise, I'm done. Thank you.
Great. Thank you so much. I think we have time for 2 questions, but I just wanted to check if there's any online. Yeah.
Excellent.
So this is from Mark Verheyen, who's attending online. In the Ursa Major supergroup, the cosmic flow forward distances of dwarf galaxy members are systematically lower than those of the more massive disks. So my question is whether your inferred Hubble constant chances when you include, changes probably, when you include only double-horned H1 profiles in your input catalog, excluding the Gaussian boxy H1 profiles.
So we haven't actually looked at doing a differentiation based on profile shape, but we certainly did put limitations in on the size and velocity line widths of the galaxies, because we too, excuse me, that's me. I've hit my limit. Because we certainly are concerned about variations in the Tully-Fisher relation once you get into the small galaxies. So we are very much constraining ourselves to the well-defined higher mass end of the Tully-Fisher relation.
Okay, so yeah, this is simple. Can you just please go to, I think, slide 8?
Slide 8, okay. I'll have to run backwards, keep talking. There we go.
Oh, yes, yeah. So I want to ask something. The contour VZ and beta, right?
Yep.
So I'm not so sure if I missed something in terms of the equations, but I just see that they're uncorrelated. Maybe can you comment on that?
Yes, so we're comparing Wallaby with CF4. So we're comparing a hemispheric sample with an all sky sample. And so the constraints in the hemisphere in directions that are not north-south, basically, is well constrained, but north-south is not well constrained by the hemispheric sample alone, which is why we would like to use DESI in the north, or indeed, of course, in the initial phases, use the CF4 as well as Wallaby in order to constrain the northern parts of the hemisphere. Yep.
Okay, well, thank you so much for a great discussion and some great questions. So we're on the home straight. And next up, we have three very talented students and former students. Hussein Munira is next. Yeah, so go ahead.
Okay, my slides up. Okay, hello everyone. My name is Munira Hussein. I am a PhD student at the University of Cape Town and the South African Astronomical Observatory, supervised by Associate Professor Sarah Blythe and Dr. Rosalind Skelton. And I'd also like to thank the African Astronomical Society for supporting my attendance at this conference. Today, I'd like to talk to you about my work measuring the neutral hydrogen, cosmic neutral hydrogen density at a redshift of 0.55 in LIDUMA, and this is work that I've done in collaboration with the wider LIDUMA team. So I thought I'd start off by re-emphasizing why neutral hydrogen gas is so important in galaxies. Neutral hydrogen connects the ionized hydrogen phases to the molecular hydrogen phases needed for galaxies to form stars. And what we've seen over the past 12 billion years or so is that the rate of cosmic star formation has peaked at a redshift of around 2 at a time called cosmic noon. And one of the questions that LIDUMA is trying to answer is whether the amount of neutral hydrogen gas available to galaxies across the cosmic history could be one of the contributors to this decrease. So the cosmic neutral hydrogen density describes how much H1 is available to galaxies or how much neutral hydrogen is available in the universe in a slice of cosmic time. At very high redshifts, there are lots of different techniques you can use to measure them, including damped climate alpha systems. However, at lower and intermediate redshifts, which we need to connect the which we need to study the evolution of omega H1, neutral hydrogen is really difficult to measure in emission because of how faint the signal is, until now that we have really cool instruments like MeerKAT and hopefully the Square Kilometer Array soon. And so the work that I've been doing is aiming to measure this using data from the LIDUMA survey, which, if you're not familiar with it, it stands for Looking at the Distant Universe with the MeerKAT Array. It is a survey on MeerKAT aiming to measure neutral hydrogen gas, or H1, in emission out to a redshift of 1.4, consisting of 324 hours in the L band and up to 3,091 hours in the UHF band. And this will hopefully be the deepest integration of H1 in emission over this frequency range. LIDUMA is a single pointing that is focused just south of the extended Chandra Deep Field South, which I'll show in a little bit. And it is a really cool survey that lets us learn a lot about neutral hydrogen. So to measure omega H1, or the cosmic neutral hydrogen density in LIDUMA, I'm looking at data in the 3 spectral windows that LIDUMA focuses on. The LIDUMA L-band data is split into these 3 spectral windows to avoid regions of RFI. For this talk, I'm focusing on, whoops, I pressed something I wasn't supposed to. Thank you. Focused on the highest redshift spectral window between 0.52 and 0.6. And I'm using a technique called stacking, just to give you a little bit of a preview of how we measure omega H1. There are typically 2 ways in the literature. You can either integrate the H1 mass function, or you can calculate the average H1 mass for your sample and multiply it by a correction factor for your sample selection. And so in this project, in this talk, I'm just going to be talking about the first method. I'm using a technique known as spectral stacking, since nobody's described spectral stacking in detail as far as I've seen today. Essentially, what you do is you take the redshift of your galaxies in your sample, you shift where you expect the 21 centimeter emission to be to the rest frame, And then you can add your several spectra together. And if your noise is Gaussian, essentially, you hope that it will go down by 1/√n, and your signal will go up by n. And so you can get a measurement of the average neutral hydrogen in your sample of galaxies, even if you're not able to detect them directly. Oh, I should also mention that the redshifts that I'm using come from the Leduma redshift catalog, which contains several different catalogs, including some proprietary Leduma spectroscopic redshifts. And this is what my sample looks like. This is all of the galaxies with spectroscopic redshifts that are good enough for stacking within the full width quarter max of the Leduma field. And these galaxies were cross-matched with the Zoet al. 2022 photometric catalog to get information like the colors and stellar masses. And this is kind of what the distribution of galaxies look like. In this work, I've restricted myself to galaxies with a stellar mass higher than 9, log stellar mass greater than 9. And yeah, this is one of the cool results that I've gotten so far. This is the stacked average H1 mass at a redshift of 0.55, which is quite amazing. We have an average H1 mass for the sample of 1.76 times 10 to the 9. And you can see it's a really cool, clear stack of 1,350 galaxies. If you want to see how this evolves in the Leduma data, please check out Lara Featherstone's talk tomorrow. She's looking at star-forming galaxies and has some cool results as well. So to measure omega H1, as I mentioned earlier, I'm going to try the mass function approach in this work. So the first step was calculating the average H1 mass in stellar mass bins. So I've stacked I think 5 samples of different stellar mass bins. And here you can see the average H1 mass for each sample. For the most part, we are kind of, except for this low mass bin, more or less quite close to the result from Bera et al. 2023 at redshift of 0.35, which is quite good, quite cool, and still a bit of a mystery why this is much lower, but I think it has something to do with our lack of completeness. Next, to try and get omega H1, as I mentioned earlier, I am summing up essentially the average H1 mass divided by the average stellar mass of each bin and multiplying by the stellar mass function from the Viper survey. This work is very, very preliminary. My preliminary banners have disappeared. So I thought I'd just give that heads up as well. This work that I'm talking about is still very preliminary. But essentially to measure this value of omega H1 that I have over here of 7.86 times 10 to the minus 4, I've essentially summed up each of these points that come from my stacks and multiplying by the stellar mass function. Oh, I'm very much ahead of time. So in my abstract, I promised I would talk about the evolution of omega H1. I haven't quite gotten to doing this analysis in the two lower redshift spectral windows, but some work by one of my colleagues, Amir Kazemi Moridani, which is, I believe, either about to be submitted or has been submitted already, has found in the in Leduma's in the lowest redshift spectral window of Leduma, looking at the detected galaxies, they found a omega H1 value of 3.09 times 10 to the minus 4. So look out for that work soon. My current results at redshift 0.55 is much higher, especially compared to other works at similar redshifts. So if you have any suggestions or ideas of why this might be, I have a couple, but I'm still looking into this. As I mentioned, this work is really preliminary, so I am ahead of time. So here is my summary. I've measured so far a very preliminary measurement of omega H1 of 7.86 times 10 to the minus 4 at an average redshift of 0.55 by summing up the H1 mass function. And some of the future work that I'm hoping to do is to, first of all, compare this result to measuring omega H1 using by looking at the average H1 mass and applying a correction factor for the selection function. Or I also want to determine corrections for confusion, which I haven't talked about at all, and improve on the error analysis. And as I mentioned, I want to extend this analysis to the lower redshift spectral windows in LaDuMA to measure that evolution. And hopefully as well, look at 3D kubelet stacking versus my results from 1D spectral stacking. Okay, yeah, thank you.
Thanks, Munira. Great talk, neat results. Maybe Munira is a bit too shy or humble to say, but she's going to be entering the job market soon. So remember this talk. I think we have time for a few questions. Hands up.
Oh, that's weird.
Hi, thank you very much. Very exciting. I'm Céline Pirou from ISO in Germany. I presume these stacking techniques relies strongly on the redshift estimates. So do I understand correctly you have spectroscopic redshifts for all of these objects? Is that correct?
Yes, so all of the objects that are in black over here have spectroscopic redshifts.
Okay, thank you.
Any more questions? We have a few at the back.
Hi, Luca Cortese from ICRA UWA. Thanks a lot. That's really nice. I'm intrigued by the difference you find with the mighty H1 stacking. Do you think it's just a difference in the sample selection, or there is something more there?
I think the sample selection is definitely one of the first things that I'm hoping to check, because I'm aware that the sample selection is star-forming galaxies only. So my sample is not restricted to star-forming galaxies. But Lara Featherstone, as I mentioned, she's going to give a talk on her work on the star-forming, similar analysis using star-forming galaxies. So I'll be working with her to compare to the mighty H1 results over here. The other thing is that there is a kubelet stacking project. So, I mean, they use kubelet stacking instead of spectral stacking. So that is something else that I want to use to compare to their work.
Thank you.
Okay, and time for one more question.
Oh, this was someone at the top.
I'm Sam from South African Radio Astronomy Observatory. Thank you for the talk. So my question is, can you go back to the plot where you're showing the histogram?
This one?
No.
Oh, the stacked spectrum,
Yeah.
yes.
So when you do the stacking, I don't know how much the beam size can impact the value of the omega H1, but can you comment on that? How do you, if it is that important, how do you optimize the value of your beam?
Yeah, so I am using, so something I kind of skipped over was that I'm extracting an aperture of 2 times the synthesized beam for each of my galaxies, and using that, the spectrum from that aperture for my stacks. I have tested this with other apertures, and as well as looking at just a single pixel, and we get similar results. So with some variation. So 2 times the beam was chosen to ensure that we get all the flux of the galaxies, because these are unresolved galaxies, especially at these very high redshifts. So we don't really want to use smaller than 2 times the beam, because that might lead us to missing out on flux.
Thanks.
Okay, let's thank Munira one more time. So penultimate talk is Francesco Senegalia.
Okay, well, welcome everybody. First of all, thanks to the organizers for giving me the opportunity to present my work today. My name is Francesco. I'm currently a postdoc at the University of Geneva, and today I'm going to present some recent work we have been doing in collaboration with many people who are actually here present today. working within the mighty H1 working group. Okay, so I don't think I need to convince this audience why we want to study H1 in galaxies. But the idea is, since a few years ago, our knowledge about H1 in galaxies was mostly restricted to the very nearby universe. And in this kind of project we wanted to go beyond the local universe and therefore basically measure H1 in galaxies at higher redshift and do that as a function of both internal and external properties of galaxies. So namely internal like stellar mass and star formation rate, and external like the large K-structure environment the galaxies live in. Manira has already excellently covered the stacking part, which plot much cuter than mine. I just want to point out one thing. So as was pointed out earlier, in order to be able to center correctly our spectra in the rest frame frequency, we do need spectroscopic redshift. So in this case also we will be selecting our sample based on galaxies with spectroscopic redshift available. Okay, all these projects are carried out with the MIGHTY survey, which is a galaxy evolution survey conducted with the Meerkat array made of 64 dishes, 13.5 meter across, located in Karoo Desert here in South Africa. MIGHTY is surveying a bandwidth between 0.9 and 1.67 gigahertz, which H1-wise means a redshift range between 0 and 0.5 approximately. The final data release will comprise 20 square degrees across Cosmos, XMM-LSS, and others, very famous ones. At this stage of this project, we were using the early science data, which were covering in the high redshift part of the data, just the Cosmos field. So here we are using data between redshift 0.23 and 0.49, basically because the high-end redshift part is dictated just by the limiting frequency, and the low redshift part, 0.23, is dictated by the limit below which the RFI becomes too strong and plagues our data, basically. Okay, so with all this in mind, we started to experiment around with the data. So we selected 9,023 star-forming galaxies with spectroscopic redshift available in the redshift range of the data, so 0.23 and 0.49. We select star-forming galaxies, as was pointed out by Manira in the earlier talk, because treasuring the lesson we learned from the nearby universe, star-forming galaxies are the one which are thought to be more H1 rich. With these galaxies, we first, you can see in the top left panel, the stellar mass distribution. In the top right panel, the redshift spectroscopic redshift distribution with a median redshift of 0.37, which is the median the redshift estimation I will be quoting hereafter. And if we stack all these 9,023 galaxies all together, we get a spectrum like the one on the bottom left panel, which is the final spectrum with a 7 sigma detection. That was the first detection we got from this data, and motivated by these results, we decided to split our sample into subsamples of stellar mass and star formation rate and specific star formation rate. So this led to basically the first detection of the scaling relations beyond the local universe. At that time, it was the first, which are shown on the series of plots on the right-hand side. So this is very dense, so I don't expect you to retain all this information. But keep in mind, okay, in these plots, the red square dots are our data point. The blue solid line is the compilation results at redshift 0 with approximately the same sample selection, so apple-to-apple comparison. And we have also overplotted with also similar selection the results from the SIMBA simulation at redshift 0 and 0.4 for comparison. And if we stick, for instance, to the top left panel, which is the very well-known and very well-studied H1 mass versus stellar mass relation, then we see that there is just a moderate evolution of scaling relations across the 4 last giga years. And also we have a good agreement with cosmological simulations. After this first work, we decided to go on and study the correlations with external properties, so basically the large K-structure. Here we are roughly using the same approach and techniques. We have just updated our stacking, and we have tried to make it more accurate. So we have implemented a more robust RFI excision procedure. And we are here 3 definitions of environment to make subselection of our sample. We are studying the H1 as a function of the galaxy over density field, meaning basically the number of galaxies that we get in the same pixel. We are studying H1 as a function of a galaxy being central, satellite, or isolated inside its host dark matter halo, and whether a galaxy belongs to the field, filament, or not. So roughly speaking, the cosmic web environment each galaxy lives in. Okay, this is for just a full sample, a 11.5 sigma detection. So we're very happy about that. And here I've plotted the results again in the H1 mass versus stellar mass plot, just to give you, again, the same context. And from left to right, you see the correlations as a function of overdensity field. So delta here is overdensity in the plots, and we choose as the threshold the value of 0, which means like dividing between underdense and overdense regions. In the left panel, you see the correlation as a function of the role inside the host dark matter halo. And on the right-hand side panel, you see the correlation as a function of the cosmic web membership, let's say. So there is roughly no correlation with the overdensity field if we choose 0 as threshold. We expect it to become more correlated if we higher the threshold for reasons that I will come now. Then there is a correlation between like the H1 amount in galaxies and the role inside the dark matter halo. But what I want to highlight here is the correlation which is present between the H1 mass in galaxies and the cosmic web environment. And here you see that the field galaxies are slightly underdense. The filament galaxies are overdense with respect to the mean, and then we have a drop of H1 in knots. That if you go and try to interpret this in a cosmological sense, it's very much in consistency with the cosmological picture according to which H1 accretes smoothly, let's say, or less non-linearly if you want, from voids to filaments. But when the H1 accretes from filaments to knots, then happens, we see the same phenomenon that has also been seen in the nearby universe, and we have seen today in talks previously. So basically H1 gets shock-heated, stripped, and other very nonlinear phenomena which strips out H1 from galaxy. Okay, finally, this is preliminary still. We tried to derive the H1 mass function and the H1 density parameter omega H1 from this data. Again, this has been excellently covered by Manira in the last talk. The idea is try to convert, in this case, we are working with stacking, so we have just one data point. So we need to figure out a way. We cannot construct the H1 mass function the way which is usually done in surveys. So the idea is to exploit the results we have from stellar mass and try to convert this into H1 mass. How do we do that? So we make two assumptions. One way is how to convert stellar mass to H1 mass, and the other is we assume that in the low redshift universe, H1 is mostly located in galaxy. So the idea is we take a complete stellar mass sample, which we can sample from an empirically measured stellar mass function. There is plenty in the literature and a good convergence on this result. And then we assume a scaling relation to convert from stellar mass to H1 mass. Now, one thing, we are no longer using the one I showed earlier, but we are using a new one, combining the MeerKAT and VLA data, which is now being submitted to ANA. And from that, we construct and now we have a synthetic H1 mass sample, so we can construct the H1 mass function the usual way and just go on and measure the omega H1 parameter. So if we look at the results, this is the resulting H1 mass function. Our result is the blue line with black dashed the fit. And then I compare both results at the same redshift, the few ones which have been measured so far, as well as the redshift 0, both in MIGHTY data and alfalfa data. So a few things I want to comment. So it's the H1 mass function, which we measure at redshift 0.37, has larger normalization than the one at redshift 0. There is an evident mismatch with the other one measured by the IAU GA team, which may be due to different things, starting from the fact that we use different scaling ratios to convert from stellar mass to H1 mass. And in general, keep in mind, we're always serving a relatively small volume. So there may be systematics, there may be cosmic variance and others. And finally, if we take all this and measure the omega H1 parameter, we see this big star, red star in the plot. So it's roughly very much in line with the global trend. It's approximately, I'm positively surprised with the value measured from Manira. So the two values are pretty much in line. It's larger than the other similar works at a similar redshift. So we have to figure out why. One thing is other works use relations at RG0 to extrapolate the results. So here we have to make some work to make a fair comparison. And with this, I end my talk. I leave you with a summary and happy to take questions.
Great talk. Any questions? So there's a question on.
It's nice to see the flattening of the H1 scaling relation of the function stellar mass, but it seems to be in tension with the GMRT scaling relation and the redshift 1, and also in tension with the recovering of the evolution of the relation at the universe mention, H1 universe mention. Could you comment on that? Why there's a sudden flattening at this redshift slice?
You mean this one, right? Yeah, the right one here. Yes. Yeah. So yeah, it's something that has been pointed out quite a number of times now. Okay, there are two things. One is, okay, we are comparing results from different telescopes over different fields and relatively smaller area. So one thing is we will never be sure unless we make a survey the same volume with the same telescope about what we are measuring. There may be systematics that we are not, both teams are not taking into account. This is one thing. And this is very difficult to dig out. The other point we have found out, and yeah, there is this paper by a PhD student in Italy, Alessandro, who is not here today, but who has just been submitted within the MIGHTY H1 working group to the journal. And what we are finding with a more accurate refinement of spectroscopic redshift is that the redshift accuracy is so important that once you try to really get rid of all the low quality, which like optical astronomy wise are still very accurate, but you really need to center very well the line, then this scaling relation gets tilted a little bit. So we recover more slope than the one we have measured here. So this work will hopefully be out very soon. And yeah, the resultant scaling relation has a steeper slope than the one we are measuring here.
Ken.
Hi, Ken Duncan from University of Edinburgh. What do you assume about the intrinsic scatter in the H1 to stellar mass ratio? Because that can have a big effect on the high mass end of the mass function when you infer it this way.
Yeah, so great point. Since we perform stacking, we have in principle no information about the scatter. So in this case, as you correctly pointed out, if you want to, of course, like make a nice sampling of the H1 mass function, I was shown by the original paper which applied this kind of technique by Apurva Bera like 2 years ago approximately. You need to model the scatter, and this is one can be you can fix it in your procedure or can be a free parameter that you can also sample. In this case, we assumed an intermediate scatter, so about this is approximately 0.3 decades. We have seen that if we vary within plus or minus 0.1 decades, it doesn't have a wild variation in the. There's as you can imagine, the variation is mostly on the very high mass end, which is important from the H1 mass function. It doesn't determine it. The impact is not a lot on the H1 density parameter because it's at the end of the day is very low probability.
I'm so sorry, we're running out of time. So I encourage you to talk to Francesco after this, but we're going to move on to our next speaker. And the final speaker. Thank you so much, Francesco. Please give him a hand. Final speaker for the day is Sambatra Rajohnson.
So hi everyone. As Brad said, my name is Sambatra Rajohnson, and I just recently finished my PhD from the University of Cape Town. And today there's a great honor for me to be able to present a part of my research at this General Assembly. So we know that galaxies are distributed in a cosmic web consisting of galaxy groups, clusters, and superclusters. And these local galaxy overdensities exert gravitational perturbations on the smoothly expanding universe, known as the overall bulk flow. But despite numerous studies, the direction and the volume where this flow seems to arise remain to be controversial. So it is thought that it is the paucity of data in, as shown in this blanked uncharted region known as the zone of avoidance, but also the volume of the surveys that actually prevent us from fully recovering this overall backflow. And later results suggest as Matricola said, there was a residual backflow beyond 16,000 kilometers per second at longitudes of around 270 degrees, close to ZOA. And this locally coincides precisely with the discovery of the Vela supercluster through optical spectroscopy, but it's in a part is still poorly mapped because it is located in the inner ZOA. And so it is not feasible in the same way, but only through H1 systematic surveys, which so far were shallow or affected by the continuum at lowest latitudes. So with my work, we therefore want to map a large unexplored area of the Vela supercluster by detecting gas-rich galaxies using Meerkat surveys. And from that, we've been using the Saro Meerkat Galaxy Plane Survey centered on the Vela region, which is 3-degree strip with a total of 90 square degrees. And in conjunction, we used the Vela H1 survey or the Meerkat Vela Supercluster survey, Vela H1, which consists of 667 fields and in total 242 square degrees, so that we can fill the gap and bridge with the available ancillary data of the Vela supercluster. So if you look into previous H1 surveys of the same Vela region, so this is what the Park's H1 zone of avoidance survey discovered in the same region. They found 131 galaxies out to 12,700 kilometers per second. But then this is what we are getting with Meerkat now. We detected more than 1,500 heavily obscured galaxies in the galactic plane with sensitivity of 0.4 to 0.8 millijansky per beam. So it is pretty amazing. And so now we're going to look into the interesting structures that we have found so far in the surveys. So if we take in, for example, the velocity range from 11,000 to 15,500. And if we look into the velocity distribution in Vela SMGPS, so we can actually see that there is a strong peak at around 12,000 kilometers per second. And when we are trying to see the on-sky plot in galactic coordinates, we can see that all the sign points in the Vela SMGPS are actually spread out over the 90 square degrees. And we want to see what does that look like in the wedge diagram, because the points that are aligned, especially here, are not necessarily aligned as a function of redshift. So it is actually looking like a very unexpected narrow filament at 12,000. But if we also still look into much more details, we can also see the blue and green dots at from this map, from the clusters AS606, AS601, and A3395, that they actually also seems to line up. So it is not yet entirely clear if this narrow filament is one contiguous filament or one or more crescent filament. Then, if we also still go to high redshift range, because our region of interest was the Vela supercluster. So now we want to see what kind of large-scale structure we are seeing at the Vela supercluster range. So if we try to look into much more details, so the cyan and green dots here are galaxies probably belonging to the first wall of the Vela supercluster. And it seems to be a filamentary structure from Abel A3391, linking up to the CISA X-ray clusters, and then linking to the blue clumps, which are partly belonging to the second wall of the supercluster, because the Vela supercluster is known to be conforming of two merging walls, but their hidden point is hidden in their core is hidden in the inner galactic plane. So it is possible that their crossing might be around this region. So if we still look into the high redshift range where the second wall of the supercluster is, so it is also possible that the crossing is actually within this region, because despite having a larger volume here, and despite having this more diffuse overdensity, because a large So a small overdensity in a large volume actually have more impact than a large overdensity in a small volume. So it is possible that the merging point could be within this region. Now, when you look into the wedge diagram of the region of the Villa supercluster, we can actually see that there seems to be an offset between the H1 and the optical near-infrared walls. So this might actually indicate that the galaxies in the Villa supercluster are still infalling toward the walls, so making those at the edge still gas-rich because they are not yet pre-processed. And by looking at the morphology of the two walls, it seems like they are possibly crossing within this region in longitudes of 273 degrees when you just look into the wedge and into the on-sky plots. And there have been recently independent reconstruction results from the Wallaby Villa data that actually pointed out the results into the overdensity of the villa walls to be also around that region. So it is quite promising. The next question that we want to answer is, how dense is that possible merging, and can we quantify this overdensity? So for that, we have here our two surveys, and we know that the detection of a galaxy is affected by the non-uniform noise distribution, the presence of RFI, and the residual continuum in our survey. So to get the overdensity through H1 mass function, we need to ensure that we are getting our complete sample from a very uniform uniform noise distribution. So we are trying to only select galaxies within the uniform noise, and by excluding all galaxies with region above 2 sigma RMS. Once that's done, then we did the rosy completeness test for our survey so that we can get the value at which our survey is complete. So the rosy completeness test assumes that there is a uniform H1 mass function as a function of the shape of the H1 mass function is uniform as a function of position. And unlike source counts, it is insensitive to large-scale structures. So basically, at a specific flux limit, it counts the number of galaxies that is brighter than the specific flux, and then it is iteratively increasing the flux limit. And for each flux limit, it gets assigned the completeness TC, and you can choose by selecting using a mean flux density or your integrated flux. And so once we got that, the flux limit from our detections, then we constructed the H1 mass functions from Villa SMGPS and Villa H1 because H1 mass function can serve as an indicator of the galaxy's environment, as it can assess the number of galaxies present per mass bins and per cubic megaparsec. And we can actually see from the log-log plot of the slope and the NEMAS that we are actually getting very similar results to the alpha-alpha H1 mass functions. We have been using the 2D stepwise maximum likelihood method, and we can see that our results, the overall fit aligns with the alpha-alpha in 3 sigma or even 2 sigma. And then the next thing we wanted to do was then to try to locate the overdensity using the H1 mass functions. So I've been just using the complete sample at the Villa supercluster range, and I've been dividing that region into 12 regions so that we can use and locate the H1 mass function for all these regions. And then by getting the ratio of the mass densities of each of the region and compare them with alpha-alpha, we are actually getting some overdensity results that actually aligns with our results, and more. And still, even additionally, we can actually see that there seems to be two regions where the two walls are actually overdense. So in the on-sky plots, we've seen that the overdensity might be around 270, 279, but with the H1 mass function plot, we can actually even see that there might be within 273 degrees, 278, and also in 272, 277 degrees in longitudes, which still supports the presence of two wall-like overdensities. So that is all very promising, but it is still preliminary estimation, so I'm still trying to calculate the uncertainty for these results. So to summarize, we have conducted over 800 meerkat pointings, over 300 square degree areas, and 2 blind systematic interferometry surveys across the thickest layer of the Milky Way. We have detected more than 1,500 heavily obscured galaxies out to 25,000 kilometers per second. We have discovered unexpected elementary structures, such as the one at 12,000 kilometers per second, and our results also supports the presence of the hits of two alike overdensities in the Vela supercluster from the on-sky plots and from the H1 mass functions. So thank you very much for your attention.
Thanks, Simbatra. So I'll note that our examiners are in the audience, so no questions for you. You guys are banned. I'm just kidding. Any questions for Simbatra? There's one at the back.
Thanks for the great talk. I just want to ask one question because you mentioned uncertainty, and I also understand that you used maximum likelihood estimator, right, to derive your uncertainties.
For which this overdensity
You have a
estimation?
plot. Yeah, you have a ellipse contour. There's a plot where we're showing that
Here.
one.
Yeah.
So my question is like, have you looked into like a Bayesian setting to derive predictive uncertainty in a Bayesian sense? Or-
No, I haven't looked into that.
Thanks.
So I'll ask a question. Betsy Adams here, but first, are there any ECRs in the audience who I can convince to ask a question? You guys have been so quiet. No, okay, everyone's tired. So you showed us some completeness, which was really cool. But I'm curious about reliability because you are in the zone of avoidance, high extinction from the galaxy. So how much do you struggle to, find a stellar counterpart and to sort of believe that your H1 detection is real and not spurious?
Yeah, so that was one of the first part. I didn't show it here. I didn't show it here, but because we are in the zone of avoidance, so there aren't, especially in the galactic plane survey, there aren't any optical and infrared counterpart. In the Vela H1, we found some cross-matching, like 20% of our detections have some infrared counterpart. So we only had to rely, especially in the GPS, only on H1 detections. So the step we were doing were on the source finding and also on looking at all the moment maps, the moment when the spectrum, and I also went one by one on Carta to look at the detections. So yeah.
I'm trying to decide if I get to qualify as an ECR, but I think it's really fantastic of getting into the zone of avoidance. And maybe riffing on that, either radio continuum or is there any possibility of getting an X-ray counterparts or looking at X-rays, either E-Rosita or some of the maybe even harder bands of looking for counterparts?
I think for the Vela H1 for those that are slightly in higher latitudes, there have been some X-ray like the CISA clusters that I've just put in here, but there aren't really, we haven't found a really like clusters around these regions, but yeah, we still need to find more.
Okay, well, I think we've run out of time. Thank you so much, Simbatra, and thank you for the speakers in this session. I will see you all tomorrow morning. Great.
Fontina isebenzi. Imike uthathile le bilapha. Danko.
that's true. I mean, I hope they realize that.
Well, it has to be.
They have their holidays, summer holidays, so they must be missing us. They'll be happy.
The opposite.
Yeah. Go probably be totally overheated. Do you go to these always?
No, this is very nice. I generally avoid these huge lakes.
I don't see this. Only. Yeah, I agree. I mean, I've never liked it. In fact, I remember that.
I mean, the only reason I've come is because people.
Yeah.
I'm also a lot of former students.
Yeah. Oh, that's
not
nice.
serious.
Yeah.
Great. I've been kind of on a partner for the thing on Saturday. Although they haven't.
I just came in on Friday.
I wanted to hear about
Excellent. You braved the weather. So did we. We had to. I know, driving was terrible. Treacherous. Yeah.
I think it's supposed to be. I've had a mushroom foraging excursion for weeks now. Maybe we would turn there.
2 weeks.
Yeah. We walked again.
Where's that? Where will that be? Oh, really? They do. Talks to you, tells you. And I was very
apparently
We thought nobody was turning. A normal person. I know.